Okay, hi everybody. So yeah, as mentioned, the title of the talk. This talk is going to be a weird talk in the sense that I want to introduce a lot of you to this area that you may not know as much about. So I'm going to talk about some of my recent work, but also a lot of work of other people, which is I think they're cool works, and so I'll still enjoy talking about that. And also there's some like ongoing work I have, and I want to mention specifically. So I have this guy, Rafrangiolo, I went to his posters for many years and just like stood bewildered, like, what is this elicitation thing? Eventually he invited me to collaborate, and then I learned what it is. And now I'm working with it and can always ask the Oracle questions. Oracle also visited this Oracle time. So yeah, like many thanks to this guy. And also, actually, Peter Grunwald is a postdoc supervisor. I also did a postdoc with Bob Williamson. He's the one who I was going to work on transfer learning when I arrived in Australia. He said, no, let's do online learning. And then he told me about mixability and all these things. And this is when I learned proper losses in like maybe 2013. So, you know, in some sense, like this talk is going to revolve around what are called proper scoring rules. And I owe like the introduction to these people. So I want to talk a little bit about something which is interesting, because I'm going to mention a website which is it's not you cannot access it in Japan because I think some kind of gambling that is not allowed. So it's interesting. I found out when trying to get the screenshot in the country. But so imagine that you would like to forecast some events around the world, okay? And keep it simple. Let's make them, events in the sense of probability, so binary outcomes, okay? And an example would be in the U.S. There's a Federal Reserve Bank, and they'll decide, whether they're going to, in this case, did I choose raise interest rates by some date, okay? And it turns out that on these websites like Predicted, there's another one which is accessible in Japan. If you want to ignore the talk and go to your laptop, then go to Polymarket. So that one does, you can access that without a VPN. So basically people can buy, shares of events, right? So if the share price is 69 cents for this Chilean presidential election winner, for 69 cents, you can buy one share. And if this person wins, right? Let's say you bought a share of this one, right? If the person wins, then you get $1 for every share that you bought, right? And so, there's real money that can be involved with these, this idea of, forecasting predictions. You can then, consider various downstream tasks, right? And let's suppose that, you don't necessarily know anything about these events, but you have access to an experts, right? As in prediction with expert advice. And what you'd like to do is somehow aggregate these experts' advice to form a forecast of your own, right? Maybe according to some notion of loss function. And I would like you to consider that, there's a particular task that you may be trying to solve. You want to do well with a current prediction task, but there might be some other downstream tasks that are of interest. And so if these experts individually have certain beliefs, meaning a given expert believes a certain person is going to win an election with probability 0.7, you would like some way to elicit the belief, meaning the expert truthfully reports that probability, and you can use those probabilities later. So for example, if you consider this forecast over here, the US is likely to increase interest rates. If you believe that's likely, maybe you're going to buy more US dollars because increasing interest rates, if I understand anything, which I probably don't about economics, this probably means the dollar is going to become more valuable, right? Now, it gets interesting with with elections, right? If you think a certain candidate is going to lose the election and you are in charge of that candidate winning, then maybe you're going to actually, in some sense, change the likelihood of that event happening by trying to spend more money, right, in countries where this is allowed, right? And so this is kind of the backdrop of this talk. Maybe, does anyone have the guess of who that is, by the way, on the right? Because I want to talk about one way of trying to elicit things from experts. So this is Michel Talleyrand. He used to have on his website, this, various mathematical problems, which I think are still there, but he used to give prizes. And he had this quote, "Become rich with my prizes," right? If somebody solves a problem, various mathematicians are competing. If someone solves it first, maybe he would check the solution and award you a prize if he thinks you solved it. And so a lot of this talk is going to be about competitions. So the idea is that suppose that you'd like to predict some outcome, okay? And some outcomes are going to be much easier to predict than others. You would like a way to reward experts that are doing particularly well given the difficulty of the outcome. So you don't just want to say anybody that gets an error which is of a certain level is going to get a certain amount of money, because for some tasks that could be easy and for others it could be difficult. Instead, what you'd like to do is say, well, if I have a collection of experts, then the ones that are at the top, right, the ones that have the highest accuracy or lowest loss, maybe one of those will be selected at random and given a prize, right? So this incentivizes people to actually seek to strive better, to try to strive to do better, right? Maybe they'll do additional research to get better beliefs about these events. And so what we're going to be talking about today are these forecasting competitions. And for simplicity, often when you have the competition, we like to give a single prize, as this makes things logistically easier. And so you can have in mind for most of this talk, even if experts are providing predictions for many, many, many events, maybe at the very end of a sequential game, there is a single prize. And that prize is related to whichever expert, in general, in some ways that will be made precise from some online learning algorithm, did the best, right? And so, you can consider forecasting competitions in an offline setting, right? Maybe experts are giving forecasts of many different outcomes simultaneously. But because, this workshop, what is the title? This online learning and online optimization, right? Online learning and optimization. So we're going to consider an online version of this game. And there's been a few papers recently that covered this online setting. And one thing that's going to be central to today is an emphasis on if an expert has a belief in the form of a probability distribution over an outcome, I would really like for the experts to be incentivized to truthfully report their belief, okay? And so we'll get into this a little bit later, but there has been a recent, it's kind of a trite expression, there's been a flurry of work in this area of omni-prediction where you would like basically to be able to get low cumulative loss or expected loss with respect to an entire collection of loss functions, right? And in that sense, it's nice if you can get the expert's underlying information and then decide how you're going to use that for different loss functions, right? So it's kind of independent interest that you can get these experts to reveal their beliefs and then use it as you see fit for different tasks, right? And I want to mention one more cell or one more kind of real world application of these forecasting competitions. So there's something called the Good Judgment Project. And basically, they would seek experts that would give probability forecasts for various global events. And in this case, people that were in the top 2% in terms of some notion of accuracy, they would be given prizes. In this case, it was kind of circular. They'd be given a prize to go to a super forecasting conference, right, of other people of that nature. Maybe the rich get richer, right? And this is a book which I haven't had time to check this out, but I think it's probably a cool book. So, okay. By the way, for this talk, it's fairly adaptive. I can skip things. You can go slowly. You can ask questions at any time if you want, especially if you forgot what some notation means and I'm using it a lot. Please just stop me. It's fine. So I think a lot of us are familiar with the classical online learning setting. And what I mean by this is really prediction with expert advice. And in particular, the situation where experts are adversarial, right? So this non-stochastic setting. And so let's just review briefly that setting. We imagine that in every round, each expert is going to provide, for today's talk, a probability forecast. And they don't necessarily have any beliefs. They don't believe in anything, right? An expert is simply trying to, together with nature or an adversary, maximize the regret of the learning algorithm. This viewpoint is adopted so that we can seek worst case bounds for the regret, right? So we're going to view experts as worst case. They don't have any internal beliefs. They're just arbitrarily selecting, their advice or reports in every round. And regret is going to be defined, as per the expert's reports. This is the expert advice. And we're going to consider a worst case analysis, right? For any sequence of the outcomes, the actual, let's say, ones and zeros for binary outcomes. And for any advice of the experts, we would like to give worst case bounds on the regret, right? So this is fairly standard. There's a nice book by Niccolo that covers this very well. There's old papers on this setting. What we're going to focus on mostly today is this other setting, which has recently been called incentive compatible online learning. That name can be a bit ambiguous, but for this talk, it's going to refer to this setting that I have here, right? So we're going to imagine that every expert, in some sense, is truly an expert. So an expert, they have formed, a belief about let's say, a probability distribution over an outcome, right? So for binary outcomes, just numbered between 0 and 1, indicating the likelihood of that outcome happening, let's say, right? And so we're going to, have experts that are really meant to be experts. And these experts have a certain behavior. So in mechanism design, you have agents that are responding to incentives. And it's convenient if we can form some notion of utility, which is directly related to an explicit payment that they're getting, okay? So I'd like for you to imagine the following setting, right? So every round, an algorithm is selecting one expert according to some probability distribution. right? So you can use hedge, exponential, weighted average forecaster, these kinds of things. And every expert, in any given round, an expert that is selected gets some fixed bag of money, okay, some fixed prize. So if you're an expert, you want to maximize how many bags of money you collect, meaning you want to maximize the sum over all rounds of the probability of being selected in each round, right? For any particular round, higher probability of being selected means higher probability of getting a prize, okay? And so this is the idea. And now if an expert has a belief about an event for a particular round, and we're imagining, the expert, when deciding what it's going to report, it is going to implicitly, if it wants to figure out its expected reward, it would compute an expectation where the outcome is drawn according to its belief. And then it's going to select the advice or the report, which tries to maximize its payoff. Okay, so the experts are going to have this sophisticated, although kind of selfish and greedy behavior. Okay, and so the reports that an expert chooses, they're going to be chosen to maximize this payment. And in this sense, because we have in mind that maybe there is an expert out there which has really good beliefs, meaning they have a very good model, a probabilistic model of how the world works. If there is such an expert, we would like to have low regret as per that expert's beliefs, okay? And this can be difficult because, experts might be lying, meaning they can report whatever they want in any given round. And if you don't set up your algorithm correctly, if the best thing for an expert to do is to actually maybe lie a lot or a little bit, then you have no hope of even identifying which expert has the best beliefs, because you only see these reports that can be very different, right? And what we're going to be doing is looking at a worst case analysis again, but it's a little bit different now. So we're still going to assume that the outcomes are, just some arbitrary sequence. The beliefs, for reasons of analysis or inability to go beyond this assumption, we're going to assume that if an expert has beliefs about outcomes in different rounds, we're going to assume that these beliefs are fixed at the beginning of the game. So this would be an oblivious adversary. However, the reports are chosen strategically, okay? So if you have a game where an expert could actually benefit in a given round by deviating from its belief, then the adversary becomes adaptive, right? So it'll be very nice if we have a system where the best thing for an expert to do is to be honest, right? So I want to mention 3 messages for this talk. One of them, it'll make sense as the talk continues, right? So there's something called competitive scoring rules. And the cool thing is these things appear to be very central in a lot of the recent work in this area of incentive-compatible online learning and also classical online learning. And to give a little bit of a teaser, if you've heard of ML Prod, this algorithm by Pierre Gaillard and other co-authors, it's going to be an example that we're going to cover later. And I think a certain version that we're going to cover actually already appeared in the Prod paper in some later section. Yeah. And we're also going to talk about some of how some of these recent results have been proved and how these results have shed light on things within classical online learning, right? So even if you don't care about incentive-compatible online learning, this perspective somehow could be meaningful. And finally, I'd like to be like an invitation for anyone who's wondering about different open problems and things to work on. Then I'm going to explicitly mention open problems as an invitation if you want to join, right? And so one thing that we're going to see is that it turns out if you think about something like hedge, right? So follow the regularized leader with the negative Shannon entropy regularizer. The update rule, it is not a linear update rule, right? Given your current weights, you multiply those by some exponential, right? It is nonlinear. It turns out that a lot of that, what we're going to see are going to be linear update rules. And this has certain advantages, right? So to give a little bit of a teaser, there's some recent results, not by me, this is by Julian Zimmertz and Theodore Marinov, where they actually get a closed form analog of follow the regularized leader with cell-less entropy. The algorithm is a little bit different, but they're able to get similar best of both worlds results for that, right? And so there's something about this, this paradigm shift to linear updating rules. It seems like you can get some cool results, okay? So I recently learned never to give the outline at the beginning, so I saved it for not the beginning. So I'm gonna give a little bit of a setup and background. What I would like to do today, one thing that maybe is different than other talks is I want to do a little bit of a little mini lecture where I try to give you various examples and build up from proper scoring rules all the way up to sophisticated algorithms and do this in terms of a sequence of things that are increasing in complexity. And so it's going to be a little bit of a history lesson. And if you've seen some of these things before, it'll be either really annoying or full of joy. I don't know. But that's where we're going to start. But before that, let me give you a concrete game protocol so that you have something in mind, right? So imagine that you are a mechanism. So a mechanism here for the talk is going to be an online learning algorithm that, it takes in information from experts, and it has some way of giving payments to the experts, okay? And so you want to forecast various events around the world, okay? And you have access to these experts, which is good because you don't know anything about how to forecast these events. And every expert, as I mentioned earlier, it'll have some fixed beliefs, okay? So for a given event, so here I'm using binary outcomes for simplicity. All this can generalize. But for a given event, right, a binary outcome, each expert will have a fixed belief about that event in the form of a probability of the event happening, okay? And we're going to have some assumption, which I find extremely annoying, and I wish we could avoid it. There is like some ability maybe to relax it, but we're going to assume that every expert believes that these events are independent, okay? This, I fully acknowledge that I don't like this assumption because we often, one of the themes of non-stochastic online learning is we want to operate with as few assumptions as possible, right? And here already making strong assumptions about the belief structure of experts, okay? But so here's the game protocol. It's going to look very similar to prediction with expert advice. So you have a number of rounds, and every round, expert is going to select his forecast or report. This is the expert advice, okay? And in general, it'd be selecting advice that lives in the space of probability distributions over the outcome. Here, we're just doing binary outcomes, so it's just 0, 1. And then a mechanism, the algorithm is going to, it's going to draw some expert IT, right, according to this probability distribution that it's maintaining and updating. If you wish, initially, let's say it's the uniform distribution. And whatever expert wins, gets drawn, they're going to get a bag of money. And using that bag of money, as the reward, they're gonna offer their reports, right? They're gonna reveal their report. In general, we'll say that all of the experts offer their reports, but you can also banditize this and say that the algorithm only gets to observe the report of the expert that was selected, right? And then, finally, nature, the world, right, decides what, if the Chilean candidate, what is it, Jara or Jara, if he's elected, right? And if that's the case, then the outcome is 1, let's say, otherwise it's 0, right? And then finally, there's going to be some loss over here. Okay, we'll talk about this in a little bit, but throughout today, the losses are always going to be what are called strictly proper losses. I'll give a definition in a second if you're not as familiar with those, right? And then, as usual, the online learning algorithm updates this distribution. Okay, and so what is the goal of this mechanism? So it would like to obtain low regret, but in particular, in blue, I have this belief regret. And so the difference here is that, so I have the cumulative loss of the algorithm on the left. That's business as usual. And you notice that the algorithm, it only has access to these reports, right? And so that's what we're going to have for the algorithm. But the algorithm would like to compare to the best expert in hindsight as per these beliefs, okay? So naturally, the algorithm would be very happy if experts were truthful so that it can actually observe, which expert had the best beliefs so far in a cumulative sense. So the sequence of beliefs is going to be determined obliviously. Yeah. So this is another annoying assumption.
Can you repeat the question?
Yeah. So Nicola asked, is the sequence of beliefs adversarial? And I'll say yes, but from an oblivious adversary. So determined at the beginning of the game. Yeah. Which it turns out a lot of the theory breaks if we don't have that in a really nasty way. Yeah. So, okay, thank you for the question. So I want to talk a little bit about this notion of belief regret and motivation for what are called mechanisms that are truthful. Because we're going to talk about approximately truthful mechanisms for a little bit, I'm always going to say exactly truthful when we mean like, the strictly best thing for an expert to do is to honestly report its belief if it wants to maximize its payments, okay? And so these mechanisms are nice because suppose that you have a system or a mechanism where somebody cannot benefit at all, at least according to the way they compute expectations, right? Their payoff is maximized by being truthful. If they know this and they trust you're actually using the mechanism you say you are, then they have no reason to spend computation deciding how to strategize. And with that saved computation, they can do different things. They could try to do research and get better beliefs. They could buy ice cream, that's fine too, right? But hopefully they do research, right, to get better beliefs, right? And that means that they're going to actually be a better expert and have a better chance of winning this competition, let's say, that is happening in every round now. Okay, and so this is something that is nice. In addition, right? So if experts are truthful, then the classical regret and the belief regret are the same, right? Because they only differed on the comparator. And if the beliefs and the reports are the same, then the comparator is the same. So that's very nice. Of course, this is not for free. You're going to have to try to design an online learning algorithm where the way the probability distribution of our experts is being updated, right, is such that an expert is going to be incentivized to be truthful. And we'll talk about how to do that in a little bit. And so finally, I have a definition of what's a strictly proper loss. It's a more general concept. I'm just dealing with binary outcomes to keep it simple. And so beliefs are simply numbers between 0 and 1, as are reports. And so what we have is that if you're an expert and you would like to, let's say that your goal is to minimize your expected loss. The way that you minimize your expected loss is to select a report which is exactly equal to the belief B, right? Anything else that you do, if you have a strictly proper loss, is going to give you a strictly higher expected loss. Okay, so this is the idea. I want to talk a little bit about one discrepancy between two different kinds of experts, and this is going to involve two different lines of work that we're going to talk about today. So one kind of expert is myopic. Now, if you think about if you took an algorithms course at some point and you have like greedy algorithms, right? Sometimes greed is good; it leads to something optimal. If you're an expert, generally a lot of us in the room, like we know something a little bit about reinforcement learning, and we know that in reinforcement learning, you don't consider experts or agents that are myopic, but you try to maximize the sum of future reward or the sum of discounted reward, right? And so generally, what we consider is non-myopic experts. Right? Experts that are, they have some sense of maximizing their cumulative wealth, and they decide what to do today by considering, the future. A myopic expert greedily, right, just considers, I want to maximize the probability that I'm selected in the next round, and that's it, right? And so these two different kinds of experts, I would say that this kind of expert, algorithm design becomes much, much, much easier, but there are some cool results that came out of that setting where you want a mechanism that is truthful for myopic experts. But I would say this is kind of more realistic, right? These are experts that, in some sense, they're strategizing in a more clever way. And so, to give you an idea of where we're going, right? So for this background, we're going to introduce a lot of these objects. But so far, we talked about a proper loss function is the same as a negative proper scoring rule. Okay? So one of them is like a reward, the other one is a loss. So we're going to first talk about those, and then we're going to introduce this mechanism, the competitive scoring rule. And from there, there's going to be a divergence. And I'm going to eventually terminate over here with this algorithm MLProd, which can be viewed as a more sophisticated version of something that appeared in this literature of incentive compatible online learning. And then on the other side, or the other divergence point, we're going to get to finally this algorithm from this paper with Junpei and my PhD student Ali Mortazavi. This is a version of Follow-the-Perturbed-Leader based on a certain notion of forecasting, or a certain kind of forecasting competition, okay? And so to start out, I want to do a little bit of history, although not too much, because I'm probably going slower than I thought I would. John McCarthy, if anyone's heard of him, he's done foundational work like all over the place, but in particular also for artificial intelligence. 1956, I think this is the first instance where we've seen the emergence of the proper scoring rule, right? So it's just like a loss except it's a reward. And later there were these like really nice, like much more detailed, the original paper was 4 pages. So there are much more detailed expositions by Bruno Di Finetti and Leonard Savage in the 1970s. So what is a proper scoring rule? So let's first say a scoring rule, it takes in a probability forecast, a number between 0 and 1 for this talk, right? And it also takes in an outcome, and then it returns a payment, okay? So it returns some amount of money that depends on these 2 arguments. Now, what does it mean for a scoring rule to be proper? We'll say a scoring rule is proper if we have the following inequality, right? So whenever you select, let's say your belief is P, if you select your report to be equal to your belief, then that is going to be a maximizer of your expected score, meaning your expected payment, okay? And anything else that you do cannot be better. And if a scoring rule is strictly proper, then we'll say that it is strictly better to choose a report that is equal to your belief, okay? So meaning if you lie, right, you would literally expect to get less payment. Okay, so that's a proper scoring rule. And the thing that is not, it's either obvious or like insightful, doesn't matter. But these scoring rules, you can view them as mechanisms, right? So they take in information and they have a way of giving a payment. And so in some sense, a scoring rule is the most basic form of a mechanism, right? So in particular, it's a truthful mechanism because if you look at that equation over there, you cannot do better by lying. And if you have a strictly proper scoring rule, then you actually will strictly do worse if you lie, okay? However, right, if you notice over here, like in life, not all of us care about expected reward, right? Some people, if you give them a gamble and with probability 0.5, they're going to get $1,002. And with probability 0.5, they're going to lose $1 million. They're like, the expected reward is positive, but not many people want to take that chance, right? So if somebody's risk neutral, then they just care about expected value. But a lot of people are not risk neutral, right? They might be risk averse, and they want to avoid situations where even with a little probability, you might lose a lot of money, okay? And so one of the disadvantages of this kind of mechanism is that it's only truthful for experts that are considering expected payment, okay? And however, the cool thing is there's a very simple trick for this, a very simple fix. And this appeared in a paper by Hossein and Okui. Okui is actually a professor at University of Tokyo, so it's around somewhere, probably within a few kilometers, I guess, in 2013. And the idea is very simple, and it's kind of cool as well. So the idea is as follows. So a scoring rule, if you have a loss function and you put a minus sign and we call it a scoring rule, right? In general, it's going to be, for the things that we're going to consider, they're going to be like continuous functions, right? And so the payment, can occupy some range from, let's keep it simple and say from 0 to 1. The binarized scoring rule does the following. So it simply takes the score, which is a number between 0 and 1. Right? You can arrange this in the case of the squared loss. Or, sorry, the squared score. I'm used to talking about losses. So the squared score, okay? 1 minus squared loss. And then you can take you can set this, this pi, which is just the score, to be the success probability for a Bernoulli distribution, right? And then you can draw W from that. And let's say if W realizes to 1, then you get a bag of money if you're the expert. And if it's 0, you do not get the bag of money. Now, it turns out that, strictly, right, any expert that likes money, right, doesn't matter if they're risk averse or risk neutral, right, doesn't matter. As long as they like money, their goal should be to maximize the probability of getting the bag of money. What is the probability of getting the bag of money? Well, that is exactly equal to their score if you condition on the outcome. But how do they compute the probability of getting the bag of money? They take a subjective expectation with respect to their belief, where the outcome is drawn according to their belief. And that gives them the probability of getting the bag of money, right? So basically, we converted this expectation, or they converted this expectation, right, score, into the probability of getting the bag of money, right? And so this way, you have this cool thing, which works even for experts that are not risk neutral, right? So it's more general. It's also a randomized scheme, right? So that could be good or bad, depending on who you are, okay? Now, there is some issue with this. So suppose that you have a collection of experts, okay? Now, if you have a single bag of money, you can say, well, I'm going to use this method of giving prizes to experts by letting every expert separately participate in this mechanism. Now, if you do that and you only have a fixed bag of money, you better divide that bag of money by n. And now nobody really cares about participating because it's much more exciting to get a big prize with a low probability than to get like this meager payment, right, with some higher probability. Let's entertain that anyways. And so there's an iteration upon this, which actually appeared earlier, because I'm going to ignore this binarization for now. We'll come back to it later. And this is called the competitive scoring rule. It's by Kilgore and Gershak in 2004, right? So much earlier than the previous idea. And so you should view this as an extension of a proper scoring rule that works as follows. So you have a bunch of experts that are competing. They're competing, okay? And just for notational reasons, to keep it simple, Sj is going to be the score of the jth expert. And so what we're going to do is we're going to say that these W's are going to be the payments that go to the experts, okay? And the payment for a given expert J is going to be their score minus the average of the other experts. Well, actually including themselves as well, okay? And so what this means is that, if you want to get a good payment, then, you need to be doing better than the average of the other experts, okay? And, like strictly, I guess, given this way, it is possible that an expert would have to get a negative payment, right? So there are ways to adjust this. You can add some like notion of subsidy, okay? But this still has the issue of requiring risk neutrality, right? Because I don't have any binarization. There's no binarization in this setup, okay? Now, the next thing I want to talk about is what is a way we can start connecting this to an online learning algorithm, okay? So suppose that there's an expert and it is wagering some amount of money, right? So it's putting, in addition to providing a report, every expert is also wagering some amount of money, and that money collectively goes into the system, and the system is going to add up all the money and then divide it across the experts. So this is called a wagering mechanism. And the particular mechanism we're going to talk about is we're going to view this competitive scoring rule as a wagering mechanism where I take exactly what we had before, exactly the same quantity over here, which could be positive or negative. I'm going to scale it. I'm going to scale it by how much a given expert wagered, how much money they put on the line, okay? And also, we're going to say that an expert, if they put in an amount of money WT, then they're going to start by getting WT, but then it can be adjusted. It can be adjusted in some way, right? And so this is turns out to be fruitful because I want you to have in mind updating a probability distribution, right? So in a little bit, this W is going to be a distribution over experts. Okay, so finally, we're going to get to this fundamental paper by many authors. So this is called the weighted score wagering mechanism. So it's a slight modification, right? So imagine that you had an online learning algorithm and every expert has a certain probability. And those probabilities for different experts currently could be different. I would like to imagine that these wagers are going to be basically the probabilities of the experts. And so it'd be convenient if every expert could put in a different amount of money, right? And so now, right, what we have, oh, wait, actually there's some issue with this. I think over here I meant to just put the wagers, just the amount of money, kind of looking ahead right now. And this is a simple modification where instead, when every expert was putting in the same amount of money, we had a simple average. Now we're going to have a weighted average, right? And it turns out, where do these formulas come from? So it turns out there's something nice about this formula. If you take the summation over the initial wagers, WJT, sum from j equals 1 through n, and if you take the summation of the new, the payments that are going out to them, these are the same, right? So this is something called budget balanced, right? And the reason that's true, you can do a tedious computation if you want, but this additive normalization is what makes it possible, right? And this additive normalization, it's a common theme in these methods that are using these linear update rules. We never have to do a division according to the new weights. They're self-normalized by this additive term. Okay. And so finally, I want to connect this to online learning. And now this is a slide that is fully correct. So I want to imagine that you have a learning rate eta. Okay. So you're an expert. You currently have probability pi jt. That's how much probability the algorithm has given you. What we're going to do is, if you have a learning rate eta, we're going to imagine the expert, it takes its probability, kind of viewed as some amount of money between 0 and 1, and it wagers an eta fraction of that. Okay, it wagers an eta fraction of that. So every expert does this. And what I'd like to view this as is an expert, it wagered an eta fraction of its money. Okay, so at the end of this round, it's still going to have a 1 minus eta fraction of its money. But in addition, for the amount of money that it put in, eta pi jt, right, it's going to get something out. If it did better than the other experts, according to this weighted sum, then its probability will increase, okay? And you can see that over here, right? So if this is a positive quantity, then the expert's probability went up a little bit, right? Otherwise, it could be 0 or it can go down, right? So this is the idea. This algorithm, it turns out to be what was called incentive compatible, or we'll say that it's an algorithm for which experts that are risk neutral are incentivized to report truthfully, okay? And one way to see that is if you look at this formula over here, if you're an expert that is myopic, okay? So you're like, well, all I want to do is maximize the probability that is assigned to me in the next round. And you look at this formula over here, the only thing that you can influence is your score. That's here, okay? The only thing that you can influence is your score. And so if you'd like to maximize the probability that you're assigned in the next round, you'd like to maximize this expected score, right? Your score also appears here, but with some weight that's in general going to be strictly less than 1, right? So that's like kind of already a connection to an algorithm that we're going to see in a little bit. And we're usually used to looking at losses like in the world of machine learning. So this is just a simple switch, and I make everything focused on losses. And here we get an algorithm, the weighted score update. I put this is the right reference. This is Rupert Freeman, a lot of other people that did nice work. So this algorithm works as follows. So framed in terms of losses, right? So it does what I mentioned it would do, right? So you take a 1 minus eta fraction of an expert's current probability, and then you add the payment. You add the payment, right? And the payment, you notice I'm packing from here. You get out this formula over here. You notice that I have a division by the sum of the probabilities. Well, that's 1. So you don't have to worry about that, right? And a simple verification is that the sum of the new probabilities is also going to be 1, right? And so that's something nice. If we didn't have the property that the sum of the new probabilities was 1, we'd have to divide. We'd have to normalize, right? And if you normalize, you're going to end up sticking losses in the denominator, and you're not going to have this property. The mechanism is no longer going to be truthful, basically, right? So it's very nice that this update rule is linear in the loss of an expert, that there is no nonlinearity. And finally, right? So I want to connect. If you're one of the people that is aware of this method MLProd from 2014, it actually can be viewed in a very similar way, except every expert also has its own learning rate A to J, right? So you can view this by now, I guess, old method MLProd, which is there are various nice things about it that I won't get into right now because it's besides the main point of the talk, but it's a really nice method. And if you let every expert have a separate learning rate, then you get what was called the MLProd update rule, which is of this form, right? And you can notice that where does the loss of a given expert J appear? Well, it appears here, and it appears here, right? And so this update rule is still going to be linear in the loss of the expert, right? So I don't know of any motivation to use this method for the problems we're talking about today, but it only gives you more power, I guess, if you could possibly use it to your advantage. Now, I want to mention one more thing. So going back to this competitive scoring rule that I talked about earlier, right? So I had a slide before where I had the competitive scoring rule, and there was branch 1. We've now done branch 1. And now I want to talk about branch 2, which means I want to talk about algorithms that are, so online learning algorithms that incentivize non-myopic experts, the ones that are truly strategizing in the way that they should. I want a mechanism which is truthful for those experts, okay? And also for the algorithm to get low regret. Okay, so starting with this competitive scoring rule, which we had before, we're going to do a trick. We're going to do that binarization trick, okay? So if every expert, right, if we're going to view every expert as getting a number between 0 and 1, and as we mentioned earlier, these numbers are going to sum to 1. So one thing that you can do is you can simply form a categorical distribution, right? And you can say, well, in any given round, right, one expert is going to get the prize, okay? So this is a similar way of doing binarization as we did the proper scoring rule. Sorry, I'm using scores again. And if you do this, then it turns out that even if an expert is for whatever risk profile an expert has, as long as they like money, then what they should do is be truthful. It doesn't matter if they're risk neutral or not. Another nice thing about this is if you're running the mechanism, if you're responsible for giving money to experts, because there's only going to be one winner in a given round, it's okay if you only have one fixed bag of money. You don't need to divide it up among the experts, right? So this solves 2 of the issues I mentioned before. And now this thing, right, binarized CSR, I'm going to view it as a building block. So what if I'm doing online learning and I have a number of events from 1 through capital T? So you can do this binarized competitive scoring rule, right, for every event. And in doing so, we're going to have these one-hot vectors, W1, W2 through WT. For every event, exactly one expert got what we're going to call a happy point. Okay, and if we do this for T rounds, and then we take a summation of all these vectors, and then take the argmax, that can be a way of deciding who the winner is. And what do you do if you are currently in round little t? You're not at the very end of the game. Well, you look at the sum of all of these win vectors so far, and you take the argmax, right? And this is with some modifications that are important. This is essentially the algorithm that Junpei, Ali, and I designed for the first no regret learning algorithm for non-myopic experts. Okay, so what I want to do now is actually maybe I should stop and see if there's any questions, because I can tell I I probably won't cover everything I wanted to cover, so it's better to see. Yeah, okay. So let me tell you a little bit about some of these recent results for the myopic expert setting. So this is a reminder of this setup, right? So you have this game of prediction with expert advice, these selfish experts, and we're going to be focused on the belief regret. So first, I'm going to consider this update rule. So the weighted score update. It's the one that I showed before. This update rule, it was derived by these people from this perspective of wagering mechanisms. And interestingly, right, it can also be connected to some pre-existing algorithms that we know about from online learning. But I think that it's kind of cool because I think these connections were not, the authors were not as aware of these connections, even though some of them are experts in online learning, but it's somehow interesting. So for myopic experts, it turns out that this method, if you've ever looked at the analysis of prod or ML prod, then it's probably not surprising. You can get regret, which is root t log n. Right? This is the case of, this is for the full information game. But somebody that spent a lot of time thinking about faster rates and statistical learning, online learning, I've recently been looking at this question of, okay, if we have a full information game, and if all the experts are incentivized to be truthful, and we're getting all of their advice, why are we selecting only one expert and using that expert's advice? If you have something like the squared loss, then it is much more natural that you take the experts, and if you were allowed to, because you don't care about truthfulness, you use the exponentially weighted average forecaster, right? And you mix together the expert's advice, and that gives you a single thing to predict, a mixed prediction, right? And that thing, if you use that, you can actually get regret, which is constant with respect to the number of rounds, right? So if you use the exponentially weighted average forecaster with, which we're not considering right now, you can get regret, which is log n over eta. Eta is this mixability constant. I just threw up this picture, but there's not enough time to maybe explain mixability. But mixability characterizes when it's possible to get constant regret for the game of prediction with expert advice. Okay, and so we're like, why should we be happy with regret, which is square root of t log n, right? Why not we say that, okay, you have all these experts, and in every round there's a probability distribution over experts, and we can still pay experts by sampling one of them and giving them the payment, but we can also use those probabilities to mix the advice together. But it's only known, as far as I know, actually be very happy if anyone knows other methods that are able to achieve a regret of this form. What we'd like to do is consider this weighted score update, or some modifications of that are still truthful, and to be able to get regret, which is, but let's say we want to get regret, which is little o of square root of t, right? So anything better than that. And so this is it's kind of ongoing work, and ironically, because I was working on this talk and teaching courses, I couldn't work on this as much as I wanted to get it done for this. But so I'm going to give you a conjecture. So some partial progress is that if you use this WSU method, like this linear updating rule, and you have a constant learning rate, it seems like you cannot get constant regret. In fact, I think we can show you can get linear regret if you do that. It's bad. You can actually track the wrong expert. Something similar is true for prod. Prod does have a normalizer. It does have a, you divide by something because it's not a self-normalizing method. The work in progress, which, I don't even know if I should call it a conjecture. I'm not even sure how much we believe it yet. But the conjecture is that there exists a way by using some intermediate learning rate that this WSU method can get regret, which is t to the 1/3, right? But this is a conjecture. It's not proven. I'm not even sure how much confidence I have in this thing. But it's if I was going to bet money, I would bet a little bit more money on this t to the 1/3 regret, right? So that's one thing which is open. Collaborator and I are working on it, but feel free if you have any ideas to talk. We're happy to work together or whatever. Yeah. So okay. So that's one part of the story. Now another part of the story in this myopic setting is for bandit feedback. So in the case of bandit feedback, right, you can the idea is that you really are going to select one expert in every round. That expert gets some money, and you only get to see the report of that expert. Realistically, this could make sense, right? Because maybe an expert only gives you the report because you paid them, right? Because you paid them. Okay. So for this method, you can try to use the same strategy as before, but using a standard trick of importance-weighted losses, right? The problem with this method is you might be able to see it, right? Because these importance-weighted losses, I'm sorry, these should be hats everywhere. These should be hats everywhere. this quantity easily could be negative, which is not allowed. You're not allowed to have negative probabilities, okay? And so you have to be careful. And so these authors, Rupert Freeman and co-authors, what they did is they considered, a standard idea, which is you incorporate some uniform exploration, and you consider the probability for a given expert is the probability from the update rule, right? And then you mix in a little bit of the uniform distribution, okay? And if you do this in the right way, and you ensure that this gamma is like, strictly smaller than eta by a certain importance amount, okay? But then you can ensure that this quantity is never going to become negative. However, somehow this idea of using uniform exploration is a bit clunky, and it seemed that the best regret that you could get was t to the 2/3, k to the 1/3, right? But t to the 2/3 is the thing to focus on. And you can spend a lot of time like trying to figure out, is the issue with the analysis or not? There was a paper by my PhD student, Ali Mortazavi, this undergrad who was at Waterloo, Canada. I don't know, I think maybe he finished now. And what we showed is that for that particular algorithm, there is no setting of these parameters, eta and gamma, such that the algorithm can get regret better than t to the 2/3, okay? And this is a case where, when you think about research, right, there's the case of people looking at the wrong thing. We were looking at the wrong thing. We were looking at the update rule, and we didn't know of any update rules that would be truthful, but we did not consider modifying, this brilliant idea from Julian Zimmerman and Theodore Marinov, that they considered modifying the estimator for the importance weighted law. They considered modifying the loss estimator, okay? And so, in some sense, the algorithm was fine if you think about decoupling the update rule from the loss estimates. And if you improve the loss estimates, then you can actually get better regret. And I'll say that using this method, WSU, the one that's been adopted to work with loss estimates, it's been adapted to work with those. They're able to get better regret. It's besides the point of this talk to look at that loss estimator, because I want to show you a cooler one that they came up with. So what is this cooler one that they came up with? So if you're familiar with follow the regularized leader with a logarithmic barrier potential, they basically used this idea to generate this linear updating rule. And one thing about follow the regularized leader with the logarithmic barrier potential is that it ends up introducing an additional probability term over here, which you wouldn't otherwise have, okay? So you take the solidus entropy. If you take I always mess this up, but you take the setting of solidus entropy that gives you logarithmic barrier, and then you get pi. You take the setting for negative Shannon entropy, and there's no pi, and you set it, this parameter to 1/2, and then you get basically the square root of pi, okay? So if you use the logarithmic barrier, you get this update rule. You notice something nice. If you believe me that this is a correct additive normalization term, the loss only appears in the numerator, okay? Loss is only in the numerator. So this thing is truthful, okay, because of the linearity of the method in terms of a proper loss function. The other thing is that you can, they showed that you can actually get regret, which is nice. So the regret bound is, I think it's the same order as the one I showed before. So ignoring log factors is square root of tk, right? Or sorry, square root of tn for n experts, okay? And one cool thing though is we have the loss estimator here. So looking at the update rule, right? So we're gonna look at this thing over here. So we have L hat JT. If you do a little bit of unpacking, we can see that, so this term over here, which is the standard importance weighted loss estimate minus the lambda t, it can be rewritten in this way. And basically this quantity, it's never gonna be very big. It's never gonna be very big. It's always gonna be in this range of -1, 1. And so this led these authors to say that in some sense, this is doing importance weighting without using importance weights. Right? And that's like it's a really cool idea. And it's a cool idea even if you don't care about this incentive compatible online learning setting. To say a little bit more about another method, so there's a solidus entropy version of this thing, which again is a linear update rule. And the main thing I want to mention for this is that you end up getting a closed form update for this method. And you're just like, well, why does that matter? Well, you're still able to get best of both worlds bounds for this method, right? So you can, in some sense, have it all. Okay, so that was the first major component of the talk. I only have 10 minutes to tell you about the things I was most excited about, which are like Junpei and Ali and my contributions. So I'll try to give a little bit of a survey of that. So let's see. It talks about myopic experts. Okay, what I want to do first is mention we should really care about non-myopic experts. They're the smarter ones. They're the ones that are doing what they're supposed to do and really maximizing their future wealth. It turns out that it's very hard to deal with those. And so we're going to make the simplifying assumption. If you're an expert and you have beliefs about events from different rounds, the strong assumption is that the expert's belief factorizes across the rounds. Okay, so this is an assumption that the events are independent. But you notice that the belief structure is very rich over here. So if you're an expert I, this R minus IT means that you're actually modeling the reports of all of the other experts, and also you're modeling the outcome. And you can model these in a way in which these things are arbitrarily highly correlated, meaning you might believe, if there's only two experts, you might believe that the other expert, their report in the last round is always equal to the outcome. These things could be random, but there could be this perfect correlation, right? And that could be part of your belief structure. So in some sense, there's some strong assumptions built in, but it's also a sophisticated belief structure. And this is a very long slide. Let me try to simplify it. So what we're going to assume, our notion of truthfulness is going to be following. So if you're an expert, if you're considering the probability of being selected in any future round, right? The way for you to strictly maximize the probability of being selected in any future round is to ensure that from the current round up until all the rounds ending at that future round, you report truthfully. If in any one of those rounds from today up until that later round where you get the payment, you lie, you're going to have strictly lower probability of getting payment. Okay? And so this is going to be our notion of truthfulness, because it is strictly better to be truthful if you want to maximize your payment in any future round, which in particular implies if you want to maximize the sum of your payments over all future rounds, then you better be truthful in all of those rounds. And I mentioned this already, this algorithm based on this thing called ELF, the Event Lotteries Forecaster. And it works as follows. Okay, so we're going to have in mind an update rule where in every round, experts are going to possibly get points that are, let's call them happy points or sad points. But in this case, right, we're going to imagine that if you're an expert, right, so if your loss is larger, then you're going to have a lower probability of getting a point for the current round. Okay, and eventually what we're going to do, right, so this is a randomized process. What we're going to do is we're going to consider whichever expert has the largest number of points, that is going to be the expert that's going to be selected in a given round. Okay, and so this is the way this forecaster works. And because we're doing online learning, we're basically always going to say that, well, if you're in some round little t, you have the data from rounds 1 through t minus 1. And so you're going to run this forecasting competition from rounds 1 through t minus 1. In every one of those rounds, some expert gets a happy point. And in round t, you look at whichever little t, whichever expert has the most happy points is going to get the prize, which means they're going to get selected. Okay, so you really should view this as an instance of Follow-the-Perturbed-Leader. At least this is convenient if you want to try to analyze this method, because at any given round, the expert that wins the lottery, right, is the one that's selected. So it is like a randomized choice. And it also, in some sense, is it's some complicated thing to actually describe the distribution over the selected expert, right? And I want to mention that this method, it appeared in a certain form originally by these authors without an analysis, but we made several changes to this method. And so to introduce some of the changes, we're going to do one thing. So in a standard lottery, right, it's nice if somebody wins the lottery, if somebody gets a point. We're going to allow something different. So we're going to get rid of this normalizer over here. And we're going to say that in any given round, at most one expert gets a point. And the probability of any particular expert J getting a point is going to be larger if its loss is larger. Okay, that's weird. Why is the probability getting larger if your loss is larger? This is going to be what I call a sad lottery, right? So a sad lottery is something that appears in this short story, The Lottery of Babylon, where when you win a lottery, you can be penalized. Okay, and it turns out to be very convenient for our analysis of this method. So you should think of these as sad points. This is the lottery you don't want to win. In some rounds, because if you take the sum over J, this is going to be less than 1. In some rounds, nobody gets penalized. But using this method, what we're going to do is in any given round, we're going to look at whichever expert has the fewest number of sad points, and that'll be the expert that is selected. Okay, so it's from these happy points to sad points. And so putting everything together, we have this method here, which we call Follow-the-Perturbed-Leader ELF, or FPL ELF. And so how does it work? Remember, W now, it stands for woe, or sadness. You can also think of this as a ruthful mechanism instead of a truthful mechanism, because ruthful means like full of sadness. So this method here, right? So we take the argmin now, whichever expert has the fewest sad points, and you can decompose the algorithm in the following way. So in every round, we're going to uniformly at random select one expert. That expert is eligible to get the sad point. This is an equivalent way of viewing the equation that I showed before. And for that expert that was selected, they're going to get the sad point with this probability. Anyone that was not the candidate, that was not set as this candidate C sub S, they will not get a sad point. And yeah, I guess there isn't a lot of time. So maybe what I'll do is I'll fast forward a little bit and say, we're able to reframe this just with a little bit of work. This is not too hard, as an instance to follow the perturbed leader, where you have the summation of these sad points over here. This is a scalar. This is the shifting. It doesn't really matter. And we can view this as a selection rule where we have the actual losses of the experts plus some zero mean noise. So there is a way to connect these, but it would take several minutes. It's easier on the whiteboard actually to show it. And once you make that connection, it turns out that there's not enough time, but that there is a way to connect this algorithm to an existing algorithm, which is simpler in many ways, which is called prediction by random walk perturbation by Luc Devroy, Gabor Lugosi, and Gergo Noy. They have a really nice analysis of this paper. So in their case, the noise is very simple, right? And it's very convenient. So in their case, the noise is always going to be basically scaled Rademacher, right? So either -1 or +1 with equal probability, except they're using -half and +1/2. And then they're able to use properties of the binomial distribution to analyze the regret of this method. And yeah, in light of time, I can't, I guess, I'm happy to talk about it offline, but I can't really get into the analysis very much. But the main thing I want to say is that in our case, the noise is much more complicated, okay? So in our case, every one of these noise random variables, it actually depends on the losses, okay? There's still going to be zero mean. There's still going to be zero mean, but this makes the analysis very nasty. And this is where, somehow, yeah, it was so possible to push through the analysis, but it adds about 30 pages to the appendix. And ultimately, we're able to get this regret bound, which we're not happy with. I hope that you're not happy with it either. Full information gain, the regret is square root of Tn log T. Why is that? Well, basically, somehow we seem to be blocked. We seem to be hitting some information theoretic limitations where no matter what we do, I'm going to try to highlight some open problem. No matter what we do, it seems like if we want a mechanism to be exactly truthful, we're not able to get enough signal from any given expert. Our sensitivity to the losses, everything that we've tried and everything that Ralph Frangillo and his students tried as well for like a year, it seems like we can't do better than this. So there is an open problem for the full information setting. Is it possible to get, ideally to get regret, which is logarithmic in n, instead of being, essentially like square root of n, like linear in n. Okay, so that's one thing. And to kind of trivialize a lot of what I mentioned in some sense, if you just want to do exponential weights, that's okay. You can do that. This will satisfy some property which is called approximate truthfulness. There's some caveats that I can't get into. There's some reasons why this does not subsume what I mentioned before. But it turns out that if you're okay with experts that lie a little bit, and you make some subtle changes to certain assumptions about the belief structure, you can have it all. You can get belief regret, which is square root of T log n. Okay, so this is kind of an intriguing thing. So in terms of complexity, is there a separation between the regret that you can get for a mechanism that is exactly truthful versus what you can get when you allow experts to lie a little bit? As long as their lies are little and cumulatively they add up to a slop, which was square root of T, it won't spoil the regret. Okay, square root of T log n, square root of T log n. Okay, and you can ask the same question about faster rates. I want to fast forward a lot just to mention the thing that I'm most excited about for all of this. So I'm going to spend like maybe 1 minute on this problem, okay? imagine the following situation, okay? So you run a political party in whatever country is allowed, you're allowed to do that for, okay? And there are two candidates. And let's say you're in charge of Groucho Marx, so one of the candidates, okay? And basically, you have experts that are reporting things, but if you receive a report from an expert that says a particular candidate is going to win with probability 0.4, you might decide as the political party that, oh, you don't like that report. You're going to invest more money in the candidate, which in some sense is going to change the world, okay? Now, what is the right notion of truthfulness in this case? Should an expert report something such that, when the world adapts to the report, the expert is truthful? This would be like a fixed point or a self-fulfilling prophecy. I personally don't like that. I think it's garbage if that's your notion of truth, but one could consider that. And you can say, like, just conceptualizing what the notion of truth is in this kind of situation is interesting. And the final thing I'll say is that, well, if you view the world as reacting to reports, an expert could be viewed as someone who is modeling how the world adapts to the report. And that is a conditional distribution, which you might try to elicit. And there are various difficulties in trying to get low regret for an online version of this problem, where you're trying to elicit these conditional distributions from experts. So, but yeah, there's not enough time. So it's just like this is strongly like a teaser. So, okay. So I think I'm just going to leave up these open problems here. I don't even know if I got to talk about some of them, but we can talk offline if you're interested to learn more. And yeah, I'll stop there. So thank you.
So thank you very much. So is there any questions?
I have a basic question. So in your problem, the expert beliefs are not observable, but can be assessed through the proper loss function or something?
Let's see. So in the full information setting,
yes,
the reports are always observable. And the outcome, even in the MANA setting, is always observable. So if you can observe the reports and the outcome, then you can observe the losses of all the experts. Right? So you actually get to directly observe these reports. But the beliefs are never observable. Yeah, they're not. So like, if you have a mechanism that is truthful, and an expert is doing what they're supposed to do, being truthful, then you can view the report as equal to the belief, and in that sense, you can say the belief is observable.
Okay, but you are considering a general case where the report and the belief can be different. Is that right?
Yeah. So if your mechanism was not truthful, then an expert might have an incentive. They might believe they'll get more. They might understand that they'll get more money if they lie. And in that case, we cannot assume that they're going to be truthful. These things could be different.
Okay.
So you can view it as that there's many different mechanisms, and we're focusing on the class of mechanisms that are truthful. You can always have an expert that is irrational, that even though they like money, they don't do anything that is in their best interest. Then we can't make any guarantees, because there's no way to judge the behavior of such an individual. So that's a problem. Yeah.
Okay, thanks.
Yeah. I've been working on, maybe we discussed this the last time we saw each other, where I can actually pay differently experts, and experts have unknown functions mapping payments to, let's say, accuracy, meaning being closer to their true beliefs. Okay, and this is like closer to, if you like, a contract theory, in which you want, the payment will elicit more effort towards on behalf of the experts to get closer. But this is a completely different problem.
So you actually paid the expert first, and you view that'll
you
map
pay
to
the expert up front, and you see how they perform, and each expert has a personalized mapping from money to performance. So you want to figure out how to spend your money in order to sort of funnel your money, channel your money towards the expert that has the chance of delivering the best prediction. Maybe some experts that you can pay them a lot, but they will always deliver garbage.
In that setting, do you generally assume that, okay, so the money will translate to some amount of effort that an expert does, but the expert will then, do you further need to make sure that they report truthfully, or that's not part of
the expert will behave according to this unknown function. Then, yeah, I guess it's fundamentally different problem.
Yeah, but I think I know like Bo Wagner has some work in this, and I don't know if he's also considered that combined with needing to incentivize them to be truthful. But yeah, if there's no payment after, then I guess they might as well be truthful. Yeah. Yeah, I guess if there's an online setting, it becomes tricky.
Okay.
Okay.
Today, I'd like to talk about recent advances on Follow-the-Perturbed-Leader for Bandit problems. So in most of my talk, I'd like to discuss the standard setting of the K-armed Bandit problems, which is a model of a gambler playing slot machines and with K-arms. And at each round, first the environment sets the loss vector of arms. Then the player puts some of the one arm, IT, and the loss only for the put arm is observed. And so the performance of the player is measured by the pseudo regret, which is the gap between the actual cumulative loss of the player and the cumulative loss of the best fixed player. And the typical goal is to minimize the regret. So here, there are mainly two settings considered in the Bandit problem. The first one is the adversarial setting, where the loss vector is determined by some possibly adaptive adversary. And it is well known that the regret is at least the square root of KT. And the second setting is the stochastic setting, where the loss is determined in IID manner from some unknown distribution PI. And it is also known that the regret is at least the order of log t over delta I, which is the gap between the optimal loss and the loss of each arm. And here, so recently, there are many researches on the policy to achieve the best of both worlds guarantee, which is the property to simultaneously achieve the both of these lower bounds. So the standard family of policy to achieve the BOBW guarantee is follow the regularized leader, or FTRL. So yeah, the name was sometimes FRL and sometimes FTRL, and I prefer the name FTRL. So here, this is the policy to put each arm randomly according to the probability vector WT, which is determined by the current unbiased estimator of the cumulative loss vector and the regularization function phi. And W is the optimal solution of this minimization problem, including the regularization term. And it is well known that the size-inf policy is the FTRA with size entropy regularizer. And it is known that it achieves the BOBW guarantee, and it also practically works very excellently. But one problem is that we need to solve this optimization, which sometimes becomes problematic depending on the applications. So in this talk, we mainly consider the Follow-the-Perturbed-Leader, or FTPA. So in this policy, we generate a random perturbation vector RT from some distribution. And then it puts a num, just minimizing the perturbed estimated loss. Each loss is perturbed by some randomized random variable. And so here, so we don't need to compute some optimization problem. So yeah, it is a very old policy, well-known policy. And for example, yeah, it is known that the square root KT log K regret is achievable under various perturbation distributions, such as the exponential distribution, Frechet-Gamble Pareto distribution, and so on. But for example, in this paper, the achievability of the optimal square root KT regret was left as an open problem. So here, so the main motivation of this work or this talk is that so when we consider the bandit problem for stochastic setting, the Thompson sampling and its variants are very widely used for its performance and very simple structured. But at the level of the research, there are also many other algorithms, and some of which have some better guarantees. But nevertheless, so yeah, as far as I know, they do not seem to become the replacements of Thompson sampling at the level of the application. And to be honest, when I also work with some company people, I mostly recommend to you just use Thompson sampling. So I feel that the simplicity and intuitiveness is also important feature. So in this sense, the S.p.A is very promising because it has a split very similar to Thompson sampling. That is just act greedily after randomization. So I believe that if theoretical guarantees for S.p.A are well prepared, then the S.p.A might be the counterpart of Thompson sampling when we consider the adversarial robustness is required. So yeah, in this talk, I'd like to introduce some recent work on this direction. The first, I'd like to introduce some fundamental property of S.p.A to achieve the BOBW guarantee for bandit problems in relation with the perturbation distributions. And then we still discuss the theoretical aspect of S.p.A, but for more practical directions, like how to make S.p.A more efficient or how to achieve the optimality of S.p.A for more complex settings. So now, before considering the optimality of S.p.A, so let me introduce the relation between S.p.A and FTRA. It is known that the S.p.A can always be expressed as the FTRA with some regularizer. For example, the S.p.A with Gambe perturbation or Gambe distribution is equivalent to FTRA with Shannon entropy regularizer, which is almost the same as the EXP3 algorithm. And but it is also known that FTRA is not always expressed as S.p.A. That is, the S.p.A is strictly included by FTRA. And there is an observation by Kim and Tewari that they say that there is no distribution reproducing the Thalessinf or Thalessinf regularizer in general. But if we consider the case of two arms, so they show that there is some corresponding perturbation and it has a fresh type tail. And from this observation, they conjectured that if S.p.A achieves the optimal adversarial regret, then it would have the fresh type tail. Now here, the word fresh type comes from the extreme value theory, which is a classic theory in statistics to discuss the distribution of the maximum of IID random variables. And it is well known that there are only possible distributions that can appear as the extreme distribution under appropriate location shift and scaling. And this comes from the fact that only the decay speed of the upper tail only matters in the extreme value theory. And here, the fresh type distribution is the second extreme distribution, which corresponds to the polynomially heavy tail, like fresh distribution or Pareto distribution or student T distribution. So now let us discuss why the extreme value theory appears in S.p.A. It is because the main important characteristic in the S.p.A is the how often or the frequency of pulling the seemingly suboptimal arms. In particular, it is important to discuss this frequency when there are many seemingly suboptimal arms. And this frequency is controlled by the decay speed of the perturbation distribution. So we can expect that the classification of distributions based on the extreme value theory would be relevant. For example, Here, the blue line is the numerically computed the perturbation distribution corresponding to Charles entropy regularizer with 2 arms, which is shown to be Fleischer type and looks like a symmetric Pareto distribution in red line, which is also a Fleischer type distribution. So from this observation, it is natural to regard this distribution just an example of Fleischer type distribution. So, in fact, we can show that if we use the Fleischer type and non-negative perturbation distribution, and if the tail index is 2, then we can show that the S.p.A achieves the best of both worlds guarantee under some mild regularity condition on the perturbation distribution. Now here, the tail index alpha corresponds to the decay rate of the tail. It becomes like this. And here, the tail index alpha roughly corresponds to 1/n alpha Charles entropy. So this result is consistent with the BOBW guarantee of Charles inf with 1/2 Charles entropy regularizer. So yeah, this largely resolves the conjecture by Kim and Tewari affirmatively. So yeah, let me briefly talk about the theoretical aspects. So here, in general, in the adversarial bandit problem, the regret is usually decomposed into 2 terms, the penalty term and stability term. And here, the stability term is important, and it corresponds to how stably the arm selection probability WT behaves depending on the estimated loss vector. And here, in FTPA, it is hard to analyze because the WT is expressed as expressed by using this function phi, expressed by this very complex expression. So by the standard analysis, the stability term is expressed by this form. So from this expression, there are many researches to discuss the relation between the derivative of phi and the phi itself, which is also called hazard rate. For example, in Abenaki, they uniformly bounded this ratio, but it led to a loose regret band containing the extra log K factor. On the other hand, in the lecture note by Bubek, so he discussed that if we can show that the phi prime over phi to the power of 3/2 is constant order, then we can show that the optimal adversarial regret. But in the FTPA, it is difficult to show this result, unlike FTRA. So our strategy is to evaluate the former ratio, like Abenaki, but in a loss-dependent form. On the other hand, so yeah, as far as I chatted with some researchers tackling the same problem, they said that they try to bound this one. So this is the main difference of our approach. And the important lemma is that under the Fleischer type perturbation, this ratio can be bounded by the square root 1/σi if Li is the sigma I smallest between the loss vectors. So the optimal adversarial regret is immediate from this lemma, and the stochastic regret bound is still a bit non-trivial, but this lemma becomes one key component. But there is one interesting observation regarding the negative result. In the results so far, so we assume that the perturbation is non-negative. So it is unclear whether this is just a technical artifact or some essential requirement. In fact, as I showed before, the perturbation distribution corresponding to Charles entropy regularizer has the symmetric distribution, which is covered by the assumption of the non-negative perturbation. So for this point, so we can show that if we consider the Fleischer type perturbation supported over entire real line with the tail index, the left and right tail index are equal, then the under some choice of the loss vector, this ratio have this lower bound. This is interesting because the former lower bound violates the required condition considered in the Vivek, and the latter lower bound does not immediately violate the use lemma, but it violates the key property used in the analysis of the stochastic regret. So these results do not immediately show the impossibility of BOBW guarantee for symmetric Frechet distributions, but the analysis based on these ratios are very common and considered to be essential. For example, the Abernathy conjecture that FTPA with Gaussian perturbation cannot achieve this regrets just due to the unbounded this ratio. So in any case, at least this result suggests that there is some limitation based on the discussion based on the just analog from FTRA with two-armed case. So far this result for the symmetric case is mostly for the theoretical interest, but it may be useful when we consider more complex setting, where when we use FTRA, more complex regularizers are used. Okay, now let's move to the second topic, FTPA for more practical directions. So here, in the adversarial bandits, the typical loss estimator is the importance weighted estimator. So which is the estimator of the loss. The zero value is assigned if the arm is not put, and if the arm I is put, then the observed loss divided by the arm selection probability is used as the unbiased loss estimator. But here there is a problem when we use FTPA, because in FTPA we do not compute the arm selection probability of each arm, so this W is not computed. So to solve this problem, so there is a technique called geometric resampling. This is a technique to unbiasedly estimate the inverse of W. But the idea is very simple, because here, so it is difficult to explicitly compute this probability, but we can simulate the process to determine this event by resampling the perturbation distribution sequentially. And to be more specific, so if the success probability of some trial is W, then we can easily see that the expected number of trials until success is 1 over W. Then by repeating resampling this perturbation until this condition is satisfied, then the number of resampling becomes the unbiased estimator of the 1 over W. But the problem is that the complexity of geometric resampling in expectation is the k-square. So this is usually worse than FTRA because it depends on the implementation. But usually in FTRA, the OK complexity is enough in most cases. So, but there can be one possibility to improve geometric resampling because the sum of resampled perturbations are clearly wasteful. For example, so let us consider the case where we want to estimate the probability of pulling the third arm when the arm 3 is the current worst arm. So in this setting, so that arm 3 is put, then the perturbation bonus for the arm 3 must be the largest compared with the other arms. So we can see that it is wasteful to resample the R3, which is smaller than the other perturbations. So based on this idea, so we constructed the improvement of geometric resampling called conditional geometric resampling. So I omit the detail, but this is a technique to just consider some narrower space to resample the perturbation. And we modify the estimator by the calibrating the number of resampling by using the probability that the perturbation comes within this area. So yeah, so this is the general idea, and there are several ways regarding how to construct this area. But by appropriately constructing the algorithm, we can show that BRBW guarantee can be obtained with the K log K average complexity. And we can also construct a version such that the worst case complexity can also be guaranteed. Regret can also be improved theoretically and empirically thanks to the reduced variance. So yeah, let me just briefly introduce the experimental results. So here we consider, so we propose two variants of the conditional geometric resampling. The first one is has a very simple implementation, and there's almost no additional implementation cost. And the second one is a bit more the complicated one, and it needs a computation of the cumulative distribution function of the perturbation, but still the complexity is K log K. And it is compared with Thalys-Inf. So the Thalys-Inf has two variants regarding the loss estimator. The first one is the importance weighted estimator I already introduced. And the second one is the reduced variance estimator. So here, this is as the name says, the variance is reduced, and it works excellently. But for the theoretical reason, its extension to S.p.A is so far difficult. We also compared the performance with the TS plot. It also appeared in the last talk. So it is a very efficient policy with the computational cost of linear computational cost. And it is a kind of algorithm related to the one-step update version of FTRL. And we consider the stochastic setting and the stochastically constrained adversarial setting, or just adversarial for short. So here, this is the result. As you can see, in this experiment, the Thalys-Inf with reduced variance estimator works the best. So the extension of S.p.A, the extension to S.p.A would be important future work, though it is so far a bit difficult. But among the estimator using the IW importance weighted estimator, the conditional geometric resampling to work the best. And on the other hand, the TS plot has the lowest computational complexity, but from the viewpoint of the regret, it does not perform not so well. And this is the result on the computational cost. So here, the TS plot is the most efficient. And on the other hand, the complexity of geometric resampling rapidly grows with K. On the other hand, when we use the complexity of conditional geometric resampling, version 1 is very similar to TS plot. And the complexity is also reasonable for the conditional geometric resampling too. Finally, I'd like to briefly mention the extension to more combinatorial settings. So originally historically the main target of S.p.A has been the combinatorial bandits, because if we use FTRL, it requires to compute the optimization over distributions over a combinatorial set, which is very complex. So for this problem, as a first step, so far we consider the M-set semi-bandits, where this is a setting where M base arms are chosen at each round. And for this setting, we show that if we use the Pareto perturbation, which is also a Fleischer type distribution, Then the regret in the adversarial setting, the regret is bounded by the square root of mkt, which is the optimal rate. And so far the stochastic regret bound is ongoing. And this is the first result to achieve the optimal adversarial regret by FTPA. And we can also show that the conditional geometric sampling is also applicable to reduce the complexity from the k square to mk log 1 plus k over n. Okay. To conclude, the first, we introduced that FTPA with Flesch type perturbation can attain the BOBW guarantee, which mostly resolved the conjecture by Kim and theory. But if we consider the perturbation supported over entire real line with symmetric decay rate, maybe BOBW guarantee is not available. Then we also discussed the practical aspects of FTPA, and we showed that the proposed algorithm of conditional geometric resampling significantly improves the regret and the computational cost, and by which maybe the FTPA is also a reasonable choice also for the simple multi-armed bandit problem, even though the main motivation of FTPA has been combinatorial bandits. And for this setting, so far, we obtained optimal guarantee for the M-set semi-bandits in the adversarial setting. So there would be many future directions. For example, I'm interested in conditional geometry resampling for other settings. Like, for example, there is a technique called matrix geometric resampling to compute the inverse of the matrix. And so it would be another important problem to consider BOBW guarantee for M-set bandit or more complex combinatorial bandit problem. Thank you very much.
Thank you.
Thank you. Right. For the combinatorial semi-bandit FTPL,
Yes.
Can't you get the same optimal with the Laplace instead of?
So it is unlikely that it is unlikely to obtain the same band. So unlike your talk, so we consider the difference of the log k factor. So so here we are considering the band without extra log factor. So in this case, it is unlikely to obtain the optimal band because, for example, Laplace distribution is a Gumbel type distribution, not Flesch type. So the tails are too light. So it is likely that the decay rate is not good for obtaining the optimal rate.
And what about full bandits? Combinatorial full bandits? Because I mean, I working on it, but I couldn't get any better than t to the 2/3 for FTPL.
Yes.
Did you try?
Yeah, so far, I tried nothing about bandits, so it is completely open. And I have no idea. So it would also be a very important program I'm interested in. But so far, I have no idea.
Any other questions?
Sorry, just quick question. FTRL for combinatorial semi-bandit can just need optimize over the distributions of the convex hull of combinatorial action.
Yeah. So, I'm sorry. In general, so if we consider the FTRS for the combinatorial bandits, so we need to consider the arm selection probability vector W over the convex hull of the combinatorial set. But the convex hull is almost equivalent to the distribution over the combinatorial set. So
set or matoroid or spanning tree, we can run the Frank-Wolf algorithms.
So depending on the structure of the combinatorial set, so there would be some efficient algorithm, so Yeah, it depends on the
okay,
setting,
yeah.
but
Yeah,
in general, so yeah, it is expressed in this way.
I don't understand the FTPL is much more efficient. It's important. Thank you.
Thank you very much. Okay, let's thank the speaker again.
So my talk will cover application of Bandit in terms of the graph mining. So today I focus on the opinion dynamics, which we focused on recently. So this talk will be based on the several papers, joint work with Federico Cinus, Atsushi Miyauchi, Francesco Bonchi. So opinion dynamics is a study where individual opinion, how the individual opinion evolve through the social interactions. So polarization and disagreement are key challenges in today's society. For example, so we will see this in political division or echo chamber, in which its users may encounter information or opinion which reflect or reinforce their own opinion. So we also see in the conflicting organization, like conflicting organization may stop the organization decision making. So the goal of this study to reduce such social division by optimizing the interventions. So this is some example. So we see like through the social interactions, your opinion may be affected by the other's opinion. Then there is suppose that there is some social network, but like there is two polarized community. So you see that the neighbor between the black community and pink community has a high disagreement. Then you see the highly polarized. So you want to avoid such a socially unstable situation. So this will find several applications. For example, building it might be helpful for building a healthier social network and guiding moderation policies or supporting consensus organization, especially for the large communities, and also creating more balanced and recommendation system. So among opinion dynamics model, we focus on Fredrickson-Johnson model of social influence. This is proposed by 1919. So in FJ model, so each individual I has an innate opinion, SI, denoted by SI, which might be latent and private, but what they express is ZI, ZIT, which may change over time due to influence from their neighbors through the interaction in the network. So formally, I'd like to define how the node-wise update or form can be written. So we start with inference network, which is in the undirected weighted graph with agency matrix A, where Wij represents how strongly user I and user J interact or how they influence each other. For user I with weighted degree Di, so the next time express opinion ZI tau plus 1 is written as follows. So this combine the two things. Like first is innate opinion and also the average expressed opinion over their neighbors. So 1 over D1 plus 1 makes sure everything normalized. So we also have this matrix form. So what makes FJ model strong is that by this node-wise update on matrix form definitions, we will reach to the unique equilibrium, which is written Z star Z star is written by I plus L inverse S, where L is the Laplacian matrix. So in short, the FJ model balance two forces, the self-belief, which is innate opinion S, and also the social influence from the neighbors. So I'd like to explain why we focus on the minimizing the metrics, polarization, and disagreement. Polarization measures how far opinions spread from the center. So polarization metric P becomes larger when the community are polarized. So assuming that the mean centered opinion, it's just the norm of the equilibrium point. Another metric is called disagreement, which measures how much opinions of connected users differ from each other. So this matrix D is it's become larger when the user I and user J, so neighbor user I and user J, has different opinions, different view, and weighted by Wij. This also has some matrix form. So key observation is here that so this matrix polarization and disagreement are mathematically useful because we can have this matrix form. Actually, it's a linear form, so it's a trace inner product. So it is helpful when we later consider the optimization framework. By minimizing this polarization and disagreement, we encourage healthier opinion dynamics, reducing extremes, and helping connected community find more common ground. So yeah, so far, so we defined our objective function f of S L is a polarization disagreement, which actually written by this form. So here S is a fix, then the optimization variable may be the intervention. So, but we see that optimization variable is now a graph Laplacian in this form. This is a network design. So in the application, the intervention might be exposure in the social network, so which might connect users across community, or participation where we encourage involvement the diverse breed users. Or maybe in the recommendation systems, the intervention might be rewriting the social feed in the online recommendation. So Musco et al. 2018 considers this offline minimizing a polarization and disagreement. So they provide a convex optimization framework, but they assume that the innate opinion S is known in advance. But in reality, this innate opinion S might be private or latent. So the platform only records express opinion, but even express opinion Z might also be incomplete or noisy. To bridge the gap, so our recent work, so we consider the query model. So we propose the optimization model where we observe a small set of exact SI values. Then using this value, we reconstruct the rest of the user's innate opinion, then optimize L offline. But here's some still limitation because this model required per user access and perfect value. It might be still impractical under noise setting. So in order to solve this limitation, so we consider online learning, so which naturally lead to the Bandit formulation. So we remove per user queries that we learn from aggregate and noisy feedback. So noisy feedback of the polarization and disagreement metric. So we reformulate our online formulation as a low-rank matrix Bandit problem, where the theta star is equal to S transpose is a hidden and latent parameter to be learned. So here is a online formulation for minimizing polarization and disagreement. So under the FJ models, we have equilibrium vector, this star. Then it can be some mathematics as we see. So polarization disagreement is written by this. Then which is trace inner product of X and theta star, where X is I plus L inverse and theta star is the latent parameter. At each round t, the learner can observe the noisy feedback. So yt is given by this, where eta t is some stochastic random noise. So here, arms are it's called forest matrices with graph-induced structure, because X is now given by I plus L inverse, where L is the Laplacian. The cumulative regret is defined by the following as a standard linear bandit. So you might think that you can just use the existing bandit algorithm, but
so XT is the matrix induced by a choice of a non-oriented graph.
Yes,
so you pick a graph that induces a identity plus L to the minus 1.
Yeah.
Gotcha. So your action space is the space of all non-oriented graphs over the same set of vertices.
And actually, we need to consider discrete action set, a K set of Laplacian, K type of Laplacian is actions.
Okay,
yeah.
okay.
But Muscato considers all the convex set. It's given by characterized by the Laplacian matrix. Yeah, maybe in another question, because this is a offline optimization definition and our formulation. So if you have question about offline setting, maybe we can. Okay, great. So yeah, so if we use the existing linear bound algorithm, when we can treat this matrix form by in the vectorized versions, full dimensional V square dimensional space, but this will use a regulate V square square root t, and it's also heavy compute. And also the existing low rank matrix usually rely on the some random Gaussian randomness, but here the arms are fresh matrices with graphs induced structure. So it's not we cannot use arbitrary design matrices here. But we can still utilize theoretical result and algorithm design from the successful line of studies from the low-rank matrix bandit, where Kyung-sok mentioned in the morning session. So it is called Explorer Subspace Then Refine framework. So our algorithm also belongs to this successful line of study. So we have two stages. So first stage is the subspace estimation. So we explore the first T1 round with uniform sampling over the action set. Then we solve the nuclear non-regularized least square. So the Kyung-sok also mentioned this. So theta hat is the minimizer of this, where the nuclear non-regularization encourage us to have the low rank matrix. Then based on the theta hat, we extract the leading eigenvector S hat. So stage 2, we will do dimensionally reduction using this information from the stage 1. So we learn linear bandit in the low dimensional space. Actually, we rotate each arm by the basis S hat, and it's also orthogonal basis. Then we get xt. Then from this xt, x prime, we construct a low-dimensional vector, which is 2v minus 1 dimension, by stacking the first entry and the rest of the first column and the rest of the first row. Now, for this low-dimensional instance, low-dimensional space, we can run the Ophel or your favorite linear bandit algorithm on these vectors. So in the theoretical analysis, restricted strong convexity is a very key feature. So we actually need for the analysis. So RSC condition is a kind of relaxation of the strong convexity of the loss function employed the stage 1. But we only need to control the some action low error constraint cone state, but definition of this cone is I omitted here. But so we only need to show that this curvature observation operator, which is the product of xt and error estimation error matrix delta theta hat minus theta star, is lower bounded by this quantity where kappa is curvature and up to tolerance parameter, which is tau, depending on the length of the first phase T1. So here our arms are finite forest matrices rather than Gaussian random matrices, but we prove that RLC condition under our setting, then the curvature is characterized by the minimum eigenvalue of ground matrix, and also we have the tolerance is the order of the dominant term is the log 1 over delta divided by T1. So here, natural boundedness is a key factor to analyze this. Our Frobenius norm of action set is always bounded by square root V, because the eigenvalue, forest matrices of the eigenvalue always lies at the interval 0 to 1. So, so based on this RSC condition, so we have following proposition for the stage 1. So when we set the suitable regularized parameter lambda T1 and the RSC condition, so we have the error bound with high probability, which is like we have the error rate at 1 over T1 as we increase the number of explanation run. Also we see that it grows only logarithmically with the number of nodes V and 1 over delta. And it becomes larger if the curvature kappa is small, that is, if the arms are purely conditioned. So we need some diversity action set. We need to have some diverse action set which is enough to estimate estimate the low rank direction. So here is the overall regret bound. So suppose that RSC condition hold with curvature parameter kappa, then our two-stage algorithm achieves that this regret bound. So Sx is the upper bound of Frobenius norm, which is upper bound square root V. Then under the some assumption, mild assumption where the kappa is satisfies some diversity action set, the dominant term becomes a V square root T, which improves the naive regret bound, which is V square root T. So in order to set the optimized T1, actually we need the signal strength, but practically we only need the lower bound of this to set T1. Then the theorem, this order of the guarantee remains same. So here's a proof sketch. So cumulative regret can be decomposed as a 3 term. So first one is the stage 1 exploration regret, which is trivially bounded by T1 because our loss are scaled to 0 to 1 without loss of generality. Then from stage 2, we have two terms. So one is the projection bias. So we extract the top eigenvalue denoted by S hat. Then let's denote the theta, it's the angle of the theta hat and theta. Then this bias is now characterized by the sine theta squared. So this can be bounded. It's the same order of the estimation error band, which is how we prove in this proposition. So then we also have the subspace bandit regret in the low dimensional space. Then due to the regret incurred by any linear bandit algorithm, so we incur the order k square root t2, which is v square root t2. Okay, so here's some simulation result on random graph. Actually, we also did some real world network, but due to the time limit, it's just enough to see this result. So blue line is offer like standard linear bandit algorithm. Also, we compare with the Oracle algorithm, which access to the true subspace estimation. So our algorithm tracks the Oracle closely and outperforms the full dimensional offer. Okay, so this is conclusion. We studied online minimization of polarization and disagreement in FJ dynamics. So we reformulate our problem as a low-rank matrix bandit with forest matrix arm set. We propose a two-stage algorithm, ESTR. Then we achieve this cumulative regret band. So future work might be to consider richer interventions. So because we consider some discretized action set. Then we also it's important to consider adaptive exploration because the curvature kappa is characterized this, but this dependence yields a pessimistic band as discussed by Kyung-Suk's talk. So this curvature is often larger, so we want to consider more adaptive exploration to remove this dependency. Thank you for your attention.
Thank you. Are there any questions?
Thank you very much. And hello, thanks a lot for your great talk. And I have a brief question. So could you go back to the slide where you introduced the curvature and curvature and tolerance of the finite forest matrices. So like here, so you proved that RSC condition holds under the uniform sampling situation.
Uniform sampling for our action set.
Action set. And like, how should I say, did you like exploited some kind of like properties of forest matrices to prove some strong curvature or tolerance based results? Or
actually, like because any forest matrix satisfies the Frobenius bound. So this is also one essential point when we use Bernstein type concentration inequality. So usually we many work consider the Gaussian random matrices. Then we can use Bernstein type constant inequality. But here, instead of this, assuming the Gaussian random matrices, we have this. Then we can actually utilize the Bernstein concentration inequality when we analyze the this tolerance parameter term.
I see. Thank you very much.
Yeah. Thank you.
Any other questions? I have a question. How can you construct a finite forest matrix in an algorithmic sense?
For example, like, so we might start with like a fixed graph network. This is like initial state, initial recommendation system. And we can use like adding the several nodes as a, like, we can encourage the friend recommendation, or maybe we can like hide, we can kind of ban some user to delete some connection. Then it can be, so this type of the addition or deletion might be the one structure for the graph network design. Then actually, we currently we only consider the K action like something which is kind of limited because we due to the second phase, we actually need to run often, so we cannot consider like all the continuous action set. But in the practical, so maybe edge addition or deletion might be the some several action set.
Okay, and as for this for the regularized leader type optimization, how can you solve this? Can you solve it by using numerically?
This is a convex optimization. Yeah, we run the standard package to solve this.
Okay, thanks. Any other questions?
Yeah, thank you for the talk. And yeah, I'd like to ask a stupid question. But so your action is the matrix, but could you explain again how the action is? But the action is in the intervention. So could you explain how the choice of the matrix is related to the intervention?
How the intervention is action space, then
so how it is related to matrix?
When we fix the Laplacian, then we like uniquely define X, I plus L inverse. This is action space. Like
so
the family of X is action set. Set of X is our action set.
So you mean that the X is related to the graph Laplacian?
Yeah,
and so it corresponds to choosing one graph.
Yeah, one graph. So
what graph corresponds to the intervention?
Okay. So
at every round, you design a graph.
We consider like action set is given by the platform, so the platform has some candidate for the intervention or like network design, which is some possible action space for each platform or recommender system can do.
And every round you choose some graph.
Then the runner will choose try to choose the like best network design from this.
I understand.
Yeah, fix the action set.
Just to follow up, I think I finally understood something. So like so for example, like Facebook or Meta might be manipulating the social network. Like that would be an intervention. They would actually like change certain edges. So the platform can do this every round.
Yeah, like platform the platform needs to specify several candidates as action before the online learning game starts.
Any other questions? Okay, then.
Thank you very much. Just to ask one more, so like, could you introduce me some, how should I say, special, so could you please go to 1 or 2 slides before, like about the definition of the problem itself? Yeah. So like.
Definition of the problem. Okay.
Yeah, so like I just want to clarify what kind of properties did you specially exploit in your analysis especially? Could you please briefly summarize like the special properties of the, how should I say, like x's in your setting? Yes.
X can be any
X.
any network.
Yeah, X can be any network, which is I plus L inverse, as you mentioned, right? And like, is there some? Does that set include all possible invertible matrices, or like it only contains certain type of matrices which satisfies?
We don't need such assumption on the Laplacian matrix. Yeah.
So which means that the resulting X, which is I plus L inverse, is also, how should I say, include various matrices. That's what. So I just want to check.
I guess I plus L inverse is uniquely defined by the X is I plus L inverse, and the original edges matrix A is uniquely defined. Yeah.
Okay. Thank you very much.
Okay, now it's time, and let's thank the speaker again.
Today, I will talk about application of online combinatorial optimization for sequential data sampling in neural network training. So first, I will introduce briefly. I mainly focus on currently. I mainly focus on the applications of online convex optimization. One is that object tracking with multiple trackers, like here. Actually, there are various online trackers, and each of them has a specialty. And so the problem is to follow a good tracker according to the target. And the difficulty is that for online tracking problem, it is difficult to get a feedback from the movie. For example, this tracker is correct or not correct. We cannot know in this at each frame. But sometimes we can get a feedback using some template matching or so. So, and we can consider that as a delayed feedback problem, and we can apply the algorithms. Another is that online pseudo labeling or weakly supervised learning. For example, in medical image segmentation, we have a large image, and we want to segment cancer or not cancer for each patch. But unfortunately, there is no patch-wise labels, and this is the weakly supervised learning problem. And so when using deep neural networks, we need to give a pseudo label for each patch. And in our framework, we adaptively give a pseudo label during the neural network training. And today's topic is that final one, data sampling in learning with noisy labels for neural networks. Okay, I'd like to talk about learning problem with noisy labels. As you may know, deep neural networks require a large number of correctly labeled samples. But many real-world data sets contain incorrectly labels, like this. For example, in this case, this sheep images has a dog label. And unfortunately, deep neural networks can easily memorize such incorrectly labeled samples. And so we need to avoid learning from these noise samples. And there are various approaches for this problem. A sampling-based approach simply aims to sample correctly labeled samples from the noisy labeled samples. A label correction approach is often combined with sampling-based approaches. For example, after sampling and after clean label sample, after avoiding noisy label samples, and noise label samples are considered as unlabeled samples. And we can use semi-supervised learning with clean label samples and unlabeled samples. And we can correct the labels of noisy label samples. And in practice, sampling-based approaches achieve good performance. But the main issues are the efficiency and the lack of theoretical supports. This is because many sampling-based approaches use a couple of DNNs, and the computation cost becomes roughly double. And let me show the minimal problem setting of our work. We consider standard multi-class classification setting with neural networks. And we have n training sets. And note that we do not know how many noise samples are included. And the final goal is to obtain a good deep neural network classifier HT after T epochs. So first of all, we consider a naive idea of this problem, our naive idea. Suppose that the training set contains k clean samples in n or whole samples. And second, we consider all possible k subsets from n original samples. So then we have a n choose k subset of samples. And thirdly, we train n choose k neural networks. We can have a trained n choose k samples. And finally, we evaluate these n choose k deep neural networks in some way, for example, using a validation sets or other way. And we obtain the best deep neural networks like this. And it should have been trained by only clean samples. But of course, as you can see, this is computationally hard and unrealistic. And motivated by this naive way, we propose a novel learning framework for noisy labels. So we consider the problem as an online K-set problem between a selection algorithm and the deep neural networks. For each epoch t, a selection algorithm gives a k-subset of samples to neural networks. And neural networks use this k-subset samples and trains. And third, the selection algorithm observes the predictions of neural networks for all samples. So it means the full information setting. This is a formal definition of the problem. For each epoch t, the algorithm selects a good dt. This indicates the selected subset. And second, neural networks is trained by this k subset of samples and update from ht-1 to ht. And third, the selection algorithm assesses the noise risk vector. Is given the selection algorithm encodes the noise risk vector theta t. We show the details later, and which is derived from deep neural networks prediction. And in this framework, the selection risk at each t can be defined as the inner dot product between dt and theta t. So you may know the answer. So, but what is the reasonable goal for selection risk? So actually, to minimize the selection risk at each epoch t is highly difficult because theta heavily fluctuates during training neural networks. And of course, the total selection risk over t is also difficult to minimize in the same reason. So it seems that a good dt is unpredictable without any statistical assumption of theta t. So as you may know, our goal is to achieve a small regret for total selection risk. The regret is defined as the difference between algorithm total selection risk and the total selection risk of the best selection risk. So as I said, theta is unpredictable, but when we consider regret minimization, we don't need to assume any statistical assumption of theta t, and we can have a theoretical guarantee of relative performance between the algorithm selection and the best selection. And in this program, we just utilize the Follow-the-Perturbed-Leader. FTPL can be also applied to combinatorial concept, and perturbations allows us to avoid overfitting to the fluctuated noise risk. And the advantage of FTPL is the efficiency. We can select the decision with linear time complexity. And we can have a theoretical support for the regret. as already known, if we set some proper eta for any sequences, the regret is bounded by this term. And so we can guarantee the gap of the selection risk, actual selection risk, and the best selection risk. And finally, we show the experimental results. And this is the important. First, we give a definition of the noise risk of each sample, like this. For example, this form indicates that if given level is predicted level with higher confidence, the given level is a correct level. On the other hand, if given level is not predicted level with higher confidence, given level is an incorrect level, which means noisy samples. And we evaluate if the designed noise risk theta is reasonable for the sample section. We use the MNIST 50% noisy samples, and we assume the ratio of noise is half of the samples is already known. And we consider 5 kinds of fixed sample section artificially. The selected case subsets, each case subset include a different percentage of noise samples. This is a perfect section and 80% clean selection, and 60% clean selection, 40% to 80%. And you can see that this result indicates that better selection achieves smaller total selection risk. And it means that our designed theta selection noise risk is reasonable in practice. And now we show the experimental settings for evaluating our sampling methods. The data sets are very common data sets, MNIST and CFA10 and CFA100 and Crazy-1M. And for MNIST and CFA10 and CFA100, we artificially made noisy level samples following the previous works. And this is the accuracy comparison. We can see that our method achieved high performance, and the noise ratio are 20%, 50%, 80%. These are the artificial random flipping, and this A14 means natural flipping. For example, airplane and a bird is flipping. And this is the bar chart of accuracy. We can see that our method is better, and in particular for highly noisy level cases, our method achieved significantly better than the baselines. And this is the result of level precision, which is the average of selected clean samples divided by k over the last 10 epochs. yeah, we can see that our method achieved a higher level precision than the state-of-the-art methods. Finally, we show other practical advantages. One is the efficiency. Our algorithm uses smaller samples than the standard learning. And the selection is done in linear time, so our algorithm is faster than other methods. And moreover, the hyperparameter eta in FPL can be fixed theoretically, and k, the number of noisy samples, can be tuned by a noisy labeled validation set. Okay, this is summary. We provide a sample selection framework for noisy, for learning with noisy labels for neural network training, and we consider as the problem as an online case problem, and it is solved by regret minimization approach. This is just an application of online convex optimization. But we can, I believe that we can extend this framework of supporting neural network training to various settings. For example, I'm currently studying hard example mining or shield labeling, as I said. And actually, the coming IBIS adaptive weight updating for curriculum learning is presented by my student. So if you see him, so please give advice. Okay, that's all. Thank you.
Thank you. So any question or comment?
Thank you for the great talk. From the experimental results,
okay.
Yeah, it can be observed that maybe the next slide. The next slide probably. Yes, thank you. From the experimental results, it can be observed that the proposed algorithm based on my learning seems the best compared to the existing approaches. So I was wondering if there is some disadvantages of the proposed algorithm compared to the existing.
So disadvantage?
Yeah, it seems like from both accuracy and computational time, the proposed algorithm is the best. So yes. I was wondering, is there any disadvantage of using the proposed algorithm?
Yeah, it's a nice question. This is so. Yeah, to be honest, I don't know why. Because our method is completely different from the classical ones. Only this decouple method, this ITLM method is based on the Follow-the-Leader based algorithm, and this is, and we can know the reason of the we can know the advantages from this method, but yeah, it is difficult to compare technically compare these co-teaching and co-teaching plus and Joker and our method.
Your algorithm is currently is still the best algorithm in the literature for dealing with noisy level data, right? So is your algorithm the best, even including the current state-of-the-art algorithms?
So actually, the current state-of-the-art algorithm is basically uses a label collection method. So, and this sampling-based approaches is basics of the label collection method. And if we achieve the state of the art, after this sampling selection, we need to try to try some semi-supervised method or unlabeled learning methods, combining this.
Can your method find a clean subset of data in a practical sense?
Yes, yes.
Did you observe that in this data set?
Actual data set?
Yeah.
We didn't check the actual data sets. Yeah, but this label precision, means that our methods can find clean samples.
I see. And then if you identify some clean data set, then can you get better accuracy by training the neural network only on the found subset?
Yes, in this sampling-based framework, we only use the clean samples.
Yeah. So your algorithm has two phases.
Yeah,
actually.
yeah. But
okay.
Yeah, in label collection methods, after this stage, we combine the clean samples and the unlabeled samples, which is originally the noisy samples.
Okay, thank you.
So we usually split the data set into a training set and validation set. And if your data is not noisy, I think the validation set is also not noisy.
Yes.
So how do you evaluate the accuracy of your method with noisy validation set?
Yeah, it's a very nice question. And in standard setting, the validation set is also noisy samples. But actually, some previous works uses a clean validation set, or I don't know why, but yeah, in this setting, at least our algorithm uses noisy validation set. And so actually, for random noise, this is not an issue, because although the validation set is noisy, the best goal is to achieve the better accuracy for validation sets, ignoring the noisy labels samples. For example, this validation set contains 60% noisy samples. The correct labels are 40%. So the maximum accuracy is 40%. So if we achieve the, if we can train on using only clean samples, we can achieve the best accuracy, 40%. But the problem is that under natural noise, maybe the 60% level noise can be learned by this natural noise in the training set. So it is a little bit the problem. Yeah, but I don't know how to avoid this problem.
So random noise means it's like independent
Yes.
noise. Okay.
Yeah.
Okay. And in those cases, that's not an issue.
Yes.
Okay. Thank you.
Okay, so if there are not any more questions, so let's thank the speaker again.
Thank you. Thank you for the introduction. And thank you for giving me an opportunity to give a talk here. Today I will talk about base correlated equilibria and no-regret dynamics. I have already uploaded my slides to my website, so please check my slides here. First, let me give you an overview of this talk. Correlated equilibrium is a very important concept, solution concept in game theory. And in online learning community, it is known that a correlated equilibrium can be reached by swap regret minimization, in which each player minimizes a regret called swap regret. This is a classical result in this field. Today's focus is communication equilibrium, which is an extension of correlated equilibrium to Bayesian games. And we also extended the notion of swap regret into untruthful swap regret for Bayesian games. And we provide upper bound, lower bound, and the price of anarchy bounds. This is the overview. So let me start with an introduction of correlated equilibrium. So let's consider an example of a game like this. There's an intersection and two cars are entering this intersection. And each car independently decides whether to go or stop. If both cars decide go, an accident occurs. If both cars chooses stop, then a deadlock occurs. If one car chooses go and the other car chooses stop, this is a good outcome. And actually, it is one of the Nash equilibria. Probably Nash equilibria is the most best known equilibrium concept in game theory. Intuitively, Nash equilibrium is a state where no one can improve their expected payoff by deviation. For example, go stop is a Nash equilibrium. The blue car can change the action from go to stop, but it just decreases his payoff. And also the red car can change his action from stop to go, but it only decreases his payoff. So this is a stable state, and it is called Nash equilibria. In this game, there are exactly 3 Nash equilibria. This one, and the symmetric one, and some randomized one. And they are all. We can see that the set of Nash equilibria is non-convex, and furthermore, it is not connected. So let's consider a more tractable solution concept, correlated equilibria. Intuitively, it is a kind of installing a traffic signal on this intersection. In the real world, the traffic signal sends a recommendation to each player. For example, the red light expresses stop signal, and the green light in English, right? Green light expresses go. And with probability 1/2, this direction is go, and this direction is stop. And with probability 1/2, this direction is go, and this direction is stop. And actually, it is an example of correlated equilibria. In contrast, in Nash equilibria, players must independently decide their decisions. In general, correlated equilibria allow the players to coordinate to correlate in any ways. So Nash equilibrium is included in the correlated equilibrium. So there are infinitely many correlated equilibria in this game. And the previous one is just a single example of this, of correlated equilibria. Formally, correlated equilibria are defined like this. This is just a formal, this is just standard definitions, standard notations for normal form games. N is a set of players we consider general N-player games. And the AI is the finite set of actions for each player, I. And A is a set of action profiles. Each action profile is a tuple of all players' actions. For example, go stop is an action profile. So each one corresponds to a single cell of the previous page, each cell of this table, payoff table. And VI is a utility function that assigns a real value to each action profile. Using these notations, we can define a correlated equilibrium as a distribution over action profiles. So this is a distribution over the payoff table cells. This distribution is called a correlated equilibrium when it satisfies these incentive constraints. For each player, I, and any deviation, phi, this player cannot improve his expected payoff. This is the incentive constraint for correlated equilibria. On the right-hand side, we consider the expected payoff of the player I if all the players follow the recommendation by the mediator, follow this distribution. On the left-hand side, all the other players follow the recommendation, but player I deviates to phi of AI instead of AI. This inequality says using any deviation phi, the player I cannot improve his expected payoff. Please note that the difference between Nash equilibria and correlated equilibria is just a correlation. If we restrict distribution to a product distribution, this definition is equivalent to Nash equilibria. Probably the notation phi is unfamiliar to you, so let me give an example. For example, this is a correlated equilibrium. Actually, this was given in the previous page. Go stop and stop go realizes with probability mod over 2 for each. Then we can consider an example of phi like this, deviation. Phi maps go to stop and stop to stop. So this means every action is mapped to stop. So the blue car always uses stop instead of the recommendation. But it only decreases his expected payoff. And any phi cannot improve the expected payoff. So this is actually a correlated equilibrium. So this is a definition of correlated equilibrium. Do you have any questions so far? Great, so let me move on to the communication equilibrium in Bayesian games. So let's consider a game like this. This is a classical example in game theory that is called Battle of the Sexes. There are two players who want to go out together next weekend, but they choose their destinations independently. There are two places in this city to visit, sea and mountain. And each player has their own preference. The blue player prefers the sea, and red player prefers the mountain. And if they can go to the same place, both can get 3 points. If they go to their preferred place, they can get 1 point. So it is much more important to go to the same place than going to the preferred place. But it is still difficult to coordinate their destinations. we have considered complete information games. So all the preferences are revealed to each other in advance. I would like to consider incomplete information games. That means not all the information is shared by the players. So here, the preference of the players is not revealed. Each player has their own type. Type represents their preference or their private information in general. And types are generated from a common prior distribution. For example, each player prefers sea or mountain with probability 1/2 for each. And each player knows their own preference, of course, but they don't know the other player's preference. However, the prior distribution of the type is known to each other from the beginning. So it is more difficult than the complete information case because they need to infer the other player's preference and to decide their action. So this is an example of a Bayesian game. So I would like to extend correlated equilibria to Bayesian games. But interestingly, there are multiple natural extensions of correlated equilibria in Bayesian games. It was surveyed by Fujii in 1993, and she provided 4 different extensions of correlated equilibria to Bayesian games. And each one corresponds to some communication protocol. Today, we focus on communication equilibria, I believe which are the most natural in terms of the communication protocol. Communication equilibria are realized by a credible third-party mediator, as in correlated equilibrium. In the first stage, each player privately tells their types to the mediator. For example, I prefer the sea or something. In the second stage, the mediator privately sends a recommendation to each player based on the reported types. For example, in this case, both players prefer the sea, so the mediator should recommend the sea to both players. Here, we consider 2 kinds of incentive constraints. In the first stage, each player must have no incentive to tell an untrue type to be better off. In the second stage, each player must have no incentive to disobey the recommendation. If both incentive constraints are satisfied, this recommendation scheme is called a communication equilibrium. I think communication equilibrium is interesting because it combines 2 very important concepts in game theory: mechanism design and correlated equilibrium. In mechanism design, such as auctions and voting, in the first stage, each player tells their types. For example, in auctions, each player tells their private valuation to the mediator as a bid. For example, I can pay at most 20 yen. But in the second stage, the mediator decides outcome that is binding, which is different from communication equilibrium. In auctions, the mediator decides who can get the item and how much they should pay. Each player cannot deviate from the decided outcome. On the other hand, in correlated equilibria, there's no type because this is a complete information solution concept. But in the second stage, each player doesn't want to deviate from the recommendation from the mediator. So communication equilibrium combines the incentive constraints from mechanism design and the incentive constraint from the correlated equilibrium. So I believe it is a natural concept for Bayesian games and information design. So let me give you the formal definition of communication equilibrium. As in the complete information case, N is a set of players, and AI is a finite action set for each player. But here we consider theta I, the set of types for each player. And as in action profiles, we consider type profiles. So each type profile is a tuple of all players' types. And as I have already mentioned, we assume a prior distribution is shared by the players in advance, which is represented by rho. Rho is a prior distribution over type profiles. And each player's utility depends not only on action profile, but also on the type profile. Using these notations, we can define a communication equilibrium. Here, a distribution pi is a type profile dependent action profile distribution. So it decides a distribution over action profile for each type profile. If this distribution satisfies this incentive constraint, it is called a communication equilibrium. On the right-hand side, we consider the case where all players follow the recommendation by the mediator. So theta is generated from the prior distribution, and action profile is generated from the distribution depending on the type profile theta I, type profile theta. Then it is just expected value for player I's utility function. On the left-hand side, we consider two kinds of deviations. First, the theta is generated from the prior distribution, but all the other players report the true type theta minus I, but player I reports psi of theta I instead of the true type theta I. So the distribution that generates action profile is different from the original one. And also, all the other players follow the recommendation with the mediator, but player I deviates to phi of theta I AI instead of the recommended AI. If any combination of these two kinds of deviations, misreporting and a deviation from the recommendation, then this distribution is called a communication equilibrium. So do you have any questions so far? Great, so let me move on to online learning part. So first, let me give you the classical result on swap regret minimization. So let me refine the definition of correlated equilibrium as an approximate version. So we restrict the range of the utility function from 0 to 1, and we consider epsilon approximate correlated equilibrium. It just means the incentive constraint is violated at most epsilon. And we consider, to compute a correlated equilibrium, we consider no regret dynamics in which each player minimizes some kind of regret. So the players repeat the same game, last T rounds. And in each round, each player decides their own mix strategy, pi IT. This is a distribution over actions. Then each player observes the reward vector, UIT. So it assigns a value, expected value for each action. Then each player obtains the expected reward according to their decided strategy. Today, all the talks consider the regret, but here we consider some different notion of regret that is called swap regret. In the repeated games, each player decides their action in each round. For example, in the first round, both players choose stop. In the second round, both players choose stop. And this is a very bad result. In almost all rounds, both players choose the same action. So an accident or deadlock. So in hindsight, the blue player regrets like, if I choose stop instead of go and go instead of stop, then I can be better off much more. So hypothetically, stop is replaced to go and go is replaced to stop. And the blue player can improve his expected payoff like this. The swap regret is defined as a difference between these two in total. Formally, the swap regret is defined like this. Please note that the ordinary regret, that is called external regret in comparison to swap regret, was defined like this. In hindsight, the player chooses the optimal fixed action. On the other hand, in swap regret, the player chooses an optimal deviation function phi. And it is known that the empirical distribution of this dynamics converges to the correlated equilibrium. So we want to minimize the swap regret. It was already solved by Blum and Mansell in 2007. This algorithm was constructed by 3 steps. In the first step, the deviation phi is expressed by a matrix Q. Q is a left stochastic matrix. And in the second step, and which is the most tricky step, the problem of selecting pi it, the action distribution, is reduced to the problem of selecting Qt, a matrix. Here, if you choose pi it action distribution as a stationary distribution of Qt, then we can replace this one by Qt pi it, and we can regard this as an external regret minimization problem, choosing Qt, a matrix. Then Qt is a stochastic matrix, so we can decompose this problem into each column. Each column is just a probability vector. So this is just an ordinary external regret minimization. And we can apply the existing result, and we can obtain this regret bound. This is the existing result for swap regret minimization. I would like to generalize this result to the Bayesian game setting. In the Bayesian game, we also consider a learning dynamics. Here, again, each player decides their strategy, but it's depending on each type. So each player decides their strategy depending on their type. Then all players' strategies are revealed to each other. This is a full information setting. And each player obtains the expected reward. Here, theta is generated from the prior distribution, and each player's action is generated from their decided strategy. Then the reward vector here is not just a reward for each action. This is a reward for each type and each action. This is an extension of online learning to the Bayesian game setting with types. Then we can also extend swap regret into untruthful swap regret in Bayesian games. Here we consider 2 kinds of deviations. Please recall the definition of communication equilibrium. We consider 2 kinds of deviations, the untruthful type reporting and deviation from the recommended action. We obtained upper bound and lower bound for this new notion of regret. Here, due to time constraints, I only introduce the upper bound result briefly. the algorithm construction is almost the same as the subregret case, but it is much more complicated. Here we need to deal with two kinds of deviations. But here we can still express two deviations as a single matrix, Q. But Q is already not a stochastic matrix. Q is kind of a combination of two layered stochastic matrix. On the first level, it is a right stochastic matrix W. And on the lower level, it is a block stochastic matrix represented by Q. Sorry, the lower level, it is a left stochastic matrix. So as a single matrix Q, it is not a stochastic matrix. Using this matrix, we can express untruthful subregret like this, similar to as in the subregret minimization. And in the next step, we can again reduce the problem of selecting xt to the selection of a matrix qt. Here Q is not a stochastic matrix, so it doesn't have a stationary distribution, but we can still, it is still possible to use the eigenvector corresponding to eigenvalue 1, and we can reduce it to the selection of a matrix Qt. And finally, we can decompose matrix Qt into small external regret minimization problems. And finally, we can obtain an upper bound like this. Using the remaining time, I would like to briefly introduce the result on the price of anarchy. It is not related to online learning. The price of anarchy is a ratio between the social welfare achieved by the worst equilibrium and the optimal social welfare. In other words, if we can lower bound the price of anarchy, it means that any equilibrium achieves a good social welfare. So we want to lower bound this. By the way, social welfare is represents the desirability of the state. As I introduced, untruthful subregret minimization dynamics converge to communication equilibrium. But actually, it converges to the intersection with agent normal form correlated equilibrium. And using this, the property of this class, we can extend the price of anarchy bounds for Bayes-Nash equilibrium to this class, intersection class. And this is an overview of my talk. In the existing result, correlated equilibrium was reached by swap-regret minimization. I extend that framework to communication equilibrium in Bayesian games. That's all from me. Thank you for listening.
Thank you. So maybe one quick question.
So can you explain the difference between communication equilibrium and Bayesian correlated equilibrium?
Oh, so actually there are many. So in existing studies, Bayesian correlated equilibrium was used for many different concepts. So which paper do you mean?
I see. Honestly, I don't know.
Yeah, actually it
so
is.
Are there papers in which communication equilibria and Bayesian correlated equilibria are the same thing? Or they are always different?
So in my understanding, there is some confusion
on
the word Bayesian communication, Bayesian correlated equilibrium. So probably it was not known that there are many different correlated equilibrium concepts in Bayesian games. And this paper is very difficult to understand, so it was not read correctly before. And the distinction between these concepts was overlooked, I think, yeah. So some paper call this one as a Bayesian correlated equilibrium, and some paper calls this one as a Bayes
And your terminology is consistent with Forge?
Forge, yeah.
Okay, cool. I have that paper. I tried to read it, yes, but it's difficult.
Yeah, I agree with
but
you.
now I will read it. I will give it another attempt.
Thank you.
Thanks.
Yeah. Thank you.
Great.
Thank you. It was really really nice talk. So I had two questions. One is, well, so your cold paper, could that be a way to get it easier to read version of Forge? Do you cover in like an easier way some of these things?
In the first part of my paper,
okay, cool.
I
so
just
it's advertising your
relied
paper. Good.
this result in a
yeah, and
easier
also
way,
like, well,
yeah.
I must have missed it. What is strategy representability? Is that something you covered before, or maybe it was?
No, sorry, it is not
Or what's the
expressed here.
Maybe the high level idea of that? Or?
So here strategy means a map like this.
Yeah.
Strategy is a map from each type to some action. So, and actually some recommendation scheme can be represented by strategy profile, but the others are not. For example, I think there's, for example, this one cannot be expressed as a strategy profile distribution. So intuitively, the recommendation to some player cannot depend on the other player's type.
Okay. No.
So as to my understanding, both like correlated equilibria or swap regret, those terminologies only consider like allocating some like probability of doing some action to wholly to another action, right?
Yes, yes.
But is there a reason that they do not like consider of like my probability of doing an action A that some like half of them goes to action B, half of them goes to action C or something?
I see.
Some settings, those I think are not considered in this work or previous works. Are there reasons?
And I believe they are equivalent. So you're considering a randomized phi, right? But it can be expressed as a randomized phi. So here you can consider a random phi here, right? But still, this is just the convex sum of the left-hand side. So if the deterministic phi cannot improve this one, then a randomized one also cannot improve this one. So in my understanding, these two definitions are equivalent, even for swap regret.
So for example, in that case, let's say phi maps both go and stop to stop.
With half probability.
Phi has some probability?
No. Phi is just a map. But you're considering, for example, you want to map go to stop and go with probability 1/2 for each, right?
True.
But these two definitions are equivalent in my understanding.
Oh, and that is captured by the probabilistic things in pi, you mean? Then? Like, how is that captured? How is it equivalent?
So, for example, you can just consider the distribution of phi, and left-hand side can be written like the expected value over phi, randomized phi.
I see. All right. Oh, okay, thank you.
Yeah, but I think, this doesn't change the definition.
Okay, so because we are running time, so let us close the talk. So let's thank the speaker again.
Thank you.